Hello everyone, this is Lecture 6 of ComSci 142, Dynamic Programming. In this video, we will discuss dynamic programming and use it to solve 4 different problems, namely minimum edit distance, longest common subsequence, longest increasing subsequence, and the knapsack problem. Now this video will be quite long since we have a lot of topics to cover, so what we'll do is we'll divide this into 3 parts, and you can watch the first 2 parts in 1 week, and you can watch the last part in the next week na. Okay? So for the first part, we'll focus on dynamic programming and minimum edit distance first. Okay? So dynamic programming is the second algorithm design paradigm that we'll discuss after divide and conquer. Now, if you remember, divide and conquer involved dividing the original problem into smaller subproblems, and we need to conquer these independent subproblems individually. Okay, so if you remember from merge sort, for example, we had something like this, wherein we divided the original problem into smaller subproblems, right? So we divided it into the left half and the right half. Okay, and these 2 subproblems were independent. Okay, so sorting the left half had nothing to do with sorting the right half. Okay, so they were independent, and after that we combined their solutions to form the original problem's solution, right? So the key point here is that in divide and conquer, the subproblems are independent of each other. Okay, so they don't they're not overlapping, they're independent. And another thing is that in general, the subproblem size in divide and conquer has the form n over b, where b could be a 2 or 3 and so on. So in merge sort, for example, the subproblem size was n over 2, right? This is also n over 2 because we are dividing it in half. Okay, so we are substantially reducing the size of the subproblem because we're dividing it. Okay, so that is for divide and conquer. But in dynamic programming, it also involves subproblems, but unlike in divide and conquer, they are not independent. Okay, in dynamic programming, we combine solutions to overlapping subproblems. So this time, overlapping ang subproblems and they're not independent anymore. So when we say overlapping, this means that the subproblems share subproblems. Okay, unlike in divide and conquer. So the subproblems are not independent anymore, and the other thing is the size is also different. So if the size in divide and conquer was n over b, here the subproblem size in dynamic programming is only n minus k. So you'll only reduce it by a little bit. So for example, in divide and conquer, if you have something like in divide and conquer, it's n over b, right? So let's say from size 8, it could go to size 4 and size 4 if you divide it by 2. But in dynamic programming, if it's n minus k, the original, if the original size is 8, it could go to a subproblem size of 7 and then subproblem size of 6. So it can only be reduced by a few items. Okay, it's not as drastic as the size change in divide and conquer. So that is the 2 basic differences for the divide and conquer and dynamic programming. First is they have overlapping subproblems instead of independent, and the size is also different. So n minus k compared to n over b for divide and conquer. Okay, so by the way, the programming part in dynamic programming means planning. Okay, so you're programming like a program in like a show's program. It's a plan. So this refers to the tabular method, as we'll see later on. So programming here does not refer to writing code. Okay, so it means more of the plan. So the basic idea for dynamic programming is remembering the past. Okay, so what does that mean? So once you solve a sub-problem once, you save the answer so that you don't have to recompute it later on. Okay? So you avoid recomputing when the sub-problem is encountered again, because remember that sub-problems are shared in dynamic programming, right? So they are common among different sub-problems. So when you encounter that same sub-problem again, you don't have to redo the computation because you've already saved the answer. Okay? So that is the main idea, remembering the past. So if you remember this, the Fibonacci algorithm, or the Fibonacci snippet from the first lecture that we had, or in our introduction to ComSci 142, we introduced the tabulation method for the Fibonacci, wherein we'll just store the previous answers in an array. So f0 is equal to 0, f1 is equal to 1, and then for the rest, for 2 up to n, we will just refer to the previous two items in the array. Okay, so we'll just remember the answers. So for example, like this, we could have something like this. So 0, 1, 2, 3, 4. So the first two items are 0 and 1. So for index 2, we will just sum up the previous two, so that would be 1. And then for index 3, we'll sum up the previous two, which is 2. And then for index 4, sum of the previous two, which is 3. So we don't need to recompute, for example, fib 1 or fib 2, because we've already computed it once, and then since we saved it, we can reuse that value later on. Okay, so that was the basic idea for tabulation. Now, what would have happened if we used a divide and conquer approach, or the recursion method? So if it was recursion, what would have happened was we would call the same function recursively, right? So for fib of 4, for example, this would call fib of 3, so 4 minus 1, and fib of 2, so 4 minus 2. And then for fib 3, this will call fib 2 and fib 1. And then this one will call fib 1 and fib 0. And then fib 2 again will call fib 1 and fib 0. But what do you notice? We are actually repeating fib 2's computation, right? Because that's computed there and that's also computed here. And since we're doing this recursively, we will have no choice but to repeat the computation, right? Because we didn't remember anything. So we actually end up doing more work than necessary. Okay, we are repeating a lot of computations. So when you have common sub-problems, it makes more sense to do the tabulation method. Okay, so save those answers to the common sub-problem so that when you encounter them again later, you will no longer need to redo the computation. Okay, so that's the basic idea for dynamic programming. So for dynamic programming, we have three basic elements. Okay, first is overlapping subproblems. Next is the optimal substructure, and third is saving answers in a table, wherein we trade space for time. So instead of redoing the computation, which takes time, we will just save it in a table or in an array, and that takes more memory, but at least we don't spend more time recomputing it. Okay, so that's saving it in a table. So we will discuss these three elements more in depth, starting with overlapping subproblems. So you already have an idea of what this means, because I've already mentioned earlier that subproblems in dynamic programming are overlapping and they're not independent. So when we break the problem into subproblems and then subproblem into subproblems, there will always be overlapping or common subproblems. Okay, so when there are overlapping subproblems in your in the problem that you're solving, it's better to use dynamic programming than divide and conquer. Okay, because you'll be able to harness the power of dynamic programming when you have common subproblems. Okay, so so as I mentioned, you use dynamic programming when the solutions to the same problems are needed over and over, and you use divide and conquer when you have solutions to different subproblems. Okay, so what we do in dynamic programming is we save the subproblem solutions in a table, because since they're overlapping, we'll have to reuse them again later. Now, what are some patterns for subproblems in dynamic programming? So I'll show you three of the most basic patterns for subproblems. So the first is the prefix pattern. So let's say that your input is like a string, or a sequence of items from 1 to n. So the subproblem could be, instead of from 1 to n, it could just be from 1 to a. So prefix, meaning the first a items. Okay, so where a can range from 1 up to n. Okay, so it would look something like this. So if you have items from 1 to 10, the prefix could be just from x1 only. It could be from x1 to x2, x1 to x3, x1 to x4, and so on. Here we have x1 to x6. So that is the subproblem. So this is a smaller problem than the original one, which is x1 to x10. Okay, so this is prefix. But in prefix, you always need to start with the first one here. So it's always from x1 up to some xa. Okay, now since it always starts with the first element, we only have n choices for the end point. So ang start only has 1, and then the end has n choices. So in total, we have n possible subproblems. So you have O of n for the number of subproblems if we follow the prefix na pattern. Okay, so that's the first one. The next one is pair of prefixes. So in pair of prefixes, this time your input would be two sequences naman, or two strings. So this time we have x and y, where x's length is length m and y's length is length n. And more or less the same lang siya sa prefix, but this time you have a pair. So it's x1 to xa, then y1 to yb. Okay, where a's range is from 1 to m, or the length of x, and b's length is from 1 to n, or the length of y. Okay, so it would look something like this. It could be that the first prefix pair is just x1 and y1, or it could be x1, x2, y1, or it could be x1 to x3, y1, or x1 to x3, y2, something like this. So it's a pair of prefix, but since it's prefix, it always starts with the first item of each sequence. So for x, how many possible prefixes are there? So from 1, start at 1, end with m. So since there are m different possible items, and then for y, start at 1, n possible choices for the end. So this is m, and this is n, and if you multiply them together, it's mn. So that's why we have O of mn different subproblems if we follow the pair of prefix pattern. Okay, so that's the second one. And then the third one is the substring pattern. So this time we only have one input again, x1 to x is our input with length n. Okay, but this time the subproblem can start anywhere. So it doesn't necessarily have to be at 1. It could start anywhere. So we have a starting point xa, and then the ending point xb, where a and b are within the range 1 to n. Okay, so it would look something like this naman. Okay, unlike in the prefix example earlier, where it always has to start at 1, this time it could start anywhere. So it could be It could start here, x2 to x6. It could start at x3. It could even just be like this lang. Okay, so the start now has n different starting points. Okay, because you could start from 1, 2, all the way up to the end. And then the end points are also n. Or actually, yeah, n man. Because you can also end anywhere, right? So n times n, that would be n squared. So there are n squared different sub-problems if you follow the substring pattern. Okay, so during the duration of this video, we will see the different patterns later, but mostly we'll see pair of prefix or the prefix pattern. Okay, so yeah, so but at least you'll be familiar with the sub-problem patterns for now. Okay, so that was the first element, which is overlapping sub-problems. The next element of dynamic programming is optimal substructure. Now, what does this mean? So, optimal substructure simply means that the optimal solutions of sub-problems contribute to the optimal solution of the problem. Okay, so just like in divide and conquer, wherein the sub-problem solutions are merged to form the bigger what do you call this, bigger problems solution. The optimal solutions of the sub-problems here are also used to create the optimal solution of the original problem. Okay, or another way to look at it is the optimal solution of the problem contains within it optimal solutions to sub-problems. Okay, so we will have to express the original problem in terms of smaller sub-problems in this case. And then finally, how will we save the data in the table? So there are actually two ways to save the data, to store the values in the table. You could either do it in the top-down strategy or the bottom-up approach. So for most of the algorithms that we'll see in this video, we will actually use the bottom-up approach. So let's start with that first. So the bottom-up approach is also known as the tabulation method. So what we'll do here is we'll build a table of values, and we will save the value of optimal solution for each sub-problems as we go. And the current value is just based on previous values. So we'll start with the base case, and once we've established the base cases, we will just each time we encounter a sub-problem, we will just refer to previous sub-problems, okay, previous values, and use that to easily compute the value for that sub-problem. Okay, so we've already seen an example of this earlier, the one with Fibonacci, fi is equal to fi minus 1 plus fi minus 2. So just look back at the previous two sub-problems, okay, in the array. Now, the second strategy is called top-down naman. So, by the way, this is called bottom-up because you start at the bottom or the base case, and then you build it up. Okay? So, you start at the bottom case, so you have 0 and 1, and then after that, you can build the bigger test cases. So, from here, you can have 1, from here, you can have 2, from here, you can have 3. So, we started from the bottom going up. The second approach, top-down strategy, also known as memoization, and yes, that's not a typo, it's really memoization, not memorization, is a combination of recursion plus a lookup table. So we'll still use recursion, but we will add a table together with it. So what we'll do is, first, let's check the lookup table. If it's not there, then we will do recursion to compute it, and then we'll save it in the lookup table, so that next time when we have to find it again, it's already saved in the lookup table. So a modified version of Fibonacci using top-down strategy will look something like this. Okay, Fibonacci of n. So first check if in the lookup table, if n is still null, meaning it's not yet saved. So if it's not yet saved, then we will have to compute it using the recursion, just like what we did in the divide and conquer. But after that, if it's already been saved, then you'll just return whatever is in the lookup table. Okay, so it's also useful for some types of problems. So when will we use top-down and when will we use bottom-up approach? We will use bottom-up if all sub-problems need to be solved at least once. Okay, so if all sub-problems have to be solved in order for you to get the original problem's solution, then we use bottom-up. And as we'll see in the later part of this video, we will mostly be using bottom-up because we'll have to solve all sub-problems for the 4 problems that we'll be looking at. But for top-down, this is appropriate if some sub-problems don't need to be solved. Okay, so if you don't need to solve everything, then just compute whichever is needed. Okay, because if for example you don't need sub-problem number 5 or 4 or 3, then if you use bottom-up, you'll just be computing them for no reason at all because you won't be using them anyway. Because in top-down, you will just need to do the recursion for whichever sub-problem you need. Okay, so that is the difference between the two and when it is appropriate to use each one. Okay, so one more thing is that most dynamic programming algorithms only compute the value of the optimal solution. Now, what does this mean? So, for example, if later on we get, if we try to find the longest common subsequence or the minimum edit distance, we won't actually find the actual subsequence for the basic DP algorithm. We'll only find the longest length or the minimum distance. So it's only the value, okay, the numerical value. If we actually want to find the optimal solution, like the actual subsequence or the actual alignment of the edit distance, to construct the optimal solution, we will need to save additional information during computation so that we can recreate the optimal solution. Okay, so there's a difference between optimal solution and the value, because the solution is the one that we are trying to find, whereas the optimal value is just like the metric or the length. Like if it's min, it's the smallest value. If it's the max, it's the biggest value. But it's not the actual solution itself. Okay, so we'll see this later on when we create an additional table for the backtrace so that we can create the optimal solution. So we will actually have another separate procedure to construct the actual solution, because for dynamic programming, it will only focus on computing the value of the optimal solution. So the length, or the metric itself. Okay, so just watch out for that, because when we build our dynamic programming tables, we will be mostly dealing with numbers. So we have to save additional information to actually create the optimal solution. Okay, so putting all of that together, these are the 4 steps for dynamic programming. So first, we need to characterize the structure of an optimal solution. So that means that how does the optimal solution look like? Okay, so we need to define it. And then after that, we need to recursively define the value of the optimal solution in terms of smaller subproblems. Okay, so we need to define the recurrence relation. And then the third is, we'll compute the value of an optimal solution in a bottom-up fashion, so using the tabular method. So this part is the easy part. After you have already, the first 2 parts are the most challenging ones. So how do you express the optimal solution in terms of smaller subproblems? So that's the real challenge in dynamic programming. But once you've established that, computing the value in the bottom-up fashion is just pretty straightforward, because you'll just be checking previous subproblems values anyway. Okay, and then the last part is optional. If you want to construct the optimal solution itself, not just the optimal value, you can also do that from the computed information using the additional data that you also saved. Okay, so those are the 4 steps for dynamic programming. Okay, now we'll be dealing with optimization problems in this video. So like minimum edit distance, so you'll find the minimum, longest increasing and longest common subsequence, so you find the longest. And then for knapsack problem, you want to find the best value. Okay, so in optimization problems, there usually are many possible solutions. Okay, so each solution has a value that is associated with it, and that is what we're trying to optimize. Okay, so we need to find a solution with optimal value. So it's either minimum or maximum depending on the type of problem that we are dealing with. Okay, and we want to emphasize that we are looking for an optimal solution, not the optimal solution, because there could be multiple optimal solutions, right? It could be more than one. So we're just looking for at least one, or just one of those optimal solutions. Okay, so yeah, just a little heads up on optimization problems. So let's now take a look at our first optimization problem that we will solve using dynamic programming, and that is the minimum edit distance. Okay, so for minimum edit distance, your input would be two sequences, x and y. Okay, so you can think of a sequence as like a string or an array of numbers. It doesn't matter, so it's just a sequence. Okay, so you have two sequences, x and y, and x's length will denote that with m, and y's length will denote that with n. Okay, so take note of that. So as I mentioned, it's usually strings, but could also be numbers. And what we're looking for is the minimum edit distance between x and y. But what does minimum edit distance mean? Okay, before we do that, we'll also need to find the best possible alignment of x and y, optional. So that is what we're trying to look for. So this is actually also known as the sequence alignment problem. So what does this mean actually? So an alignment is just a way of writing strings one above the other. So one word on top of the other, and we are trying to align or match the letters, okay, or the items. And the alignment allows us to measure distance or similarity between two strings. So let's see an example. So we have two words here, snowy and sunny. Okay, so we could align snowy and sunny like this, snowy and then sunny, and then you'll notice there are blanks. Okay, or we could also align it like this, so you'll also notice there are blanks. The goal is to try to align as many letters as possible so that there will be common letters or common items, and we're trying to minimize the number of edits. Okay, so like this one, this is a difference, this is different, this is different. So the cost of this is only 3 because we have a difference of 1, 2, and 3 here. But if you align it this way, wherein you did not align S and S here, there would be an additional cost of +2. So because we have S aligned with a blank, S aligned with U, so that's 2, 3, 4, and then 5, right? So this one has a different cost if you align it this way. Okay, so the blanks indicate gaps, and any number of gaps can be placed anywhere in either string. So you could put as many blanks in there as you want in the alignment. Okay, and the cost of the alignment is just the number of columns in which the characters differ. So as I showed you earlier, so we have 1, 2, 3, and then we have 1, 2, 3, 4, 5 here as the cost. So how many columns do they differ? So that is the cost of the alignment. So for minimum edit distance, we're trying to find the best possible alignment, and the minimum edit distance is the cost of that best possible alignment. Okay, so the best alignment is the one that minimizes the cost, so the smallest possible edit. So the minimum number of edits to change string 1 to string 2. Okay, so an edit could be an insertion, a deletion, or a substitution. So in this one, in this example, this one is an insertion. Okay, wait. This one is an insertion because from a blank you inserted the U, right? This one naman is a deletion. Why is that? Because from W it became blank. So in turn, you kind of deleted W in the next word. And then this one is a substitution because you replaced O with N. Okay? So here, from blank to U, it's an insertion. From W to blank, it's a deletion. And from O to N, it's a substitution. Okay, so those are the three different types of edits that you can do. Okay, so why are we interested in solving this problem? So it has some applications, like for spell checkers. So it would suggest words close to the misspelled words, and how do you know that that word is close to the misspelled word? Well, you can get the edit distance. Okay, if it's close enough, then you can suggest that one. And also in bioinformatics, so in analyzing DNA strings, so you have a long list of A, T, C, and G strings, and then if you have two DNA strings, you can find their similarity by getting their edit distance. Okay, if it's a small edit distance, then that means that it's more or less similar. Otherwise, they are different. Okay, so there are useful applications for minimum edit distance. So the minimum edit distance was first studied in way back 1965, also known as the Levenshtein distance, while the dynamic programming algorithm was created or discovered or published in 1974 by Wagner and Fisher. So Wagner-Fisher algorithm. So before we look at the dynamic programming approach, let's take a look at how the brute force will do it. Okay, so for brute force, we will try to generate all possible alignments of X and Y and compute the cost of each alignment and return the alignment with the least cost, right? So pretty straightforward because it's brute force. The problem is it's very inefficient because there are too many possible alignments, right? Even for like a small sized set of words like A, B, C, and C, A, let's say A, B, B. You could align it like this, so A, B, C, A, B, B, or you could align it like this, C, A, B, blank, B, then blank, or you could align it like this, A, B, C, blank, A, blank, B, blank, B, then blank. So there's way too many possible alignments for you to be able to solve this efficiently. Okay, so we cannot, or it's not wise to generate all possible alignments and compute their cost and find the least cost. So we will use dynamic programming to solve minimum edit distance efficiently. Okay, so for the dynamic programming solution, first we need to find out what are the sub-problems and what are the overlapping sub-problems, and we need to check whether the sub-problems follow the optimal substructure. Okay, that means that they contribute towards solving the original problem. So for the sub-problems in minimum edit distance, we will use the pair of prefixes because our inputs are a pair of strings, right? X and Y. So our input is X with the length 1 up to M. So X1, X2 up to XM. And we have another input, the second word, Y1, Y2 up to YN. So that is the length. Okay? So for the sub-problems, we will consider their prefixes. So we'll call the prefix for X, we'll call it 1A, and for Y, 1 up to B. So for the prefix, it would be X from 1 up to A, where A ranges from 1 up to M. So it could be anywhere from 1 up to M. And then for Y naman, Y1 up to YB, where B ranges from 1 up to n. Okay, so we'll just look at the prefix. So it could be like this, or just here, and so on. Okay, so we will denote this with the equation minimum edit distance of AB. This means that it's the minimum edit distance of x from 1 up to A and y from 1 up to B, meaning the prefix. Okay, so this prefix and this prefix. So if it's minimum edit distance from A to B, we are referring to the prefixes. Okay, and our goal later on is to find the original one, which is med of m and n, because that is the length of x and y respectively. Okay, so that's the subproblem. Now the next step is to express this problem in terms of smaller subproblems. But how do we do that? So what do we know about the best possible alignment of x from 1 to A and y from 1 to B? Well, we're not sure, right? But what we do know is that there are 3 possible alignments of x 1 to A and y from 1 to B. It could be like this. So it could be XA aligned with the blank. The last column could be blank aligned with YB, or the two are aligned. Okay, so like for example, if our test case was, let's say, ABC and DEF, in this case that would be ABC aligned with maybe there's a blank here. So it could be like this, wherein the last item of XA is aligned with a blank. Or it could also be like this, wherein it's ABC blank and then DEF. So it was the last item of YB aligned with a blank, like this. Okay? Or it could also be like this, wherein the two are aligned. So we don't know which of the 3 will give us the best possible answer, right? Because it could be this one or this one or this one. So yeah, we don't know. So we'll have to check each one. Okay? So let me just erase this one first. Okay. Okay, so we will have to look at each one. So in the first case, wherein we aligned XA with a blank. So what will this mean? If it was XA with a blank, so X1, X2, X3 ... and then A minus 1 XA, and then aligned with a blank. So it could be Y1, Y2, Y3, YB here, and then aligned with a blank, right? So if we align XA with the blank, there is a cost of 1 because this is a deletion, right? So since we deleted, we will have to add a cost of 1, right? And then what would be the rest of the subproblem? So after taking care of this one, the rest of the subproblem would be solving the alignment of x1 up to xa minus 1 na lang because we've already done xa. And then for y, from y1 to yb still. Okay? So we need to align 1 up to a minus 1, and then for y, 1 up to b. Again, nga nag a minus 1 na lang siya. It's because we've already aligned xa with the blank. So, this last part is already done. So, we will just take care of 1 up to a minus 1 this time. And what is this in terms of this one? In terms of the our equation MED here. So, this is actually minimum edit distance from a minus 1 to b na lang. Okay? So, minimum edit distance of a minus 1, b. Because we need to align the rest of x without xa, and then the full y to b. Because we did not take anything from y, because we just aligned it with a blank. So that is the first test case. Okay? But what if this time it's already blank and yb? If it's blank and yb, it would look like this. So x1, x2, x3, dot, 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 xa, and then there's a blank here. Then y1, y2, y3, dot, 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 yb minus 1, and then yb. Right? So we aligned blank with yb. So if we align blank with yb, this also has a cost of 1 because this is an insertion, right? So there's a cost of 1, and then what about the rest of the subproblem? So we will need to align x1 up to xa and y1 up to b minus 1 na lang. Okay, because we've already done yb. So from x1 to a, y1 to b minus 1, that would be MED of a and b minus 1. Okay? So, earlier, sa case 1, we had MED of a minus 1 b plus the cost of 1 because of the deletion. Right? For case number 2, this is now MED of a b minus 1 and then plus 1 again because of the insert. Okay? So, AB minus 1 ang second test case. Now, for the third test case, what would happen? Okay, so let me erase this one first. Okay, so this time, what if we align xa and xa and yb? So let's say from x1 up to xa minus 1, and then xa here, b minus 1 yb. So we align the two. Now what would be the cost of this one? Is it automatically 1? Well, we're not yet sure. If they are not the same, then it has a cost of 1. But if they are the same, then the cost would be 0, right? Because if we align, let's say, A with B, something like that, this will have a cost of 1. This is a substitution. But if it's A and A, for example, this has no cost because this is the same. So that is a cost of 0. So the cost of this alignment is dependent on whether they are equal. Okay, earlier we added the plus 1 immediately because it was a deletion and an insertion. We were sure that would cost 1. But here we are not sure because it would depend on whether they are the same letter or not. Okay, so it's still dependent, but in other versions this even has a cost of 2 if mismatched, because basically it's similar to two steps like deletion plus insertion, right? If you substitute. But for our version, we'll just stick with cost is equal to 1 just to keep things uniform. Okay? Now, how about the rest? After we aligned xa with yb, the rest of the sub-problem would be from x1 up to xa minus 1 and then y1 to yb minus 1. So that would be MED of a minus 1, b minus 1. Okay, because we are now aligning up to the a minus 1, b minus 1 of both strings. Right? So for case 3, that would be MED of a minus 1, b minus 1 plus either 0 or 1, depending on whether they are different or not. Okay? So it's optional ang plus 1 kung ano siya, kung different ang letters. Okay? So those are the 3 test cases. But how would we know? So we've already established the sub problems, the smaller sub problems, no? So from the original problem of MED AB, we've established that we can express it using the smaller sub problems. So for example, we have wait, let me just erase this one first. Okay, so we've established that MED can be expressed in terms of MED A minus 1B here, AB minus 1, and A minus 1B minus 1. And these are all smaller subproblems because for this one, this has a smaller A, this one has a smaller B, and this one both has a smaller A and B. Right? So, smaller siya kay AB in general. But, how would we know which one is the correct alignment or the best alignment? So, we don't know. It could be this one, it could be this one, or it could be this one. So, what we'll do is we'll try all of them and pick the best. Okay? So, try all of them and pick the best. So, if we put everything together, this is the this is how the sub-problem of minimum edit distance AB will look like. So, this is for case 1, A minus 1B, and then the plus 1, the cost. And then for case 2, AB minus 1 plus 1. For case 3, A minus 1B minus 1, plus the difference of AB. So, difference of AB is 0 if they are the same. Otherwise, it would be 1. So, this could be either 0 or 1 ang diff of AB. And then, since we don't know which one gives us the best answer, we'll get all 3 values and then we'll get the minimum because we're trying to find the minimum edit distance, right? So, get the minimum out of the 3 values. So, we have now expressed the bigger subproblem in terms of smaller subproblems. Okay? So, for example, let's take a look at a subproblem like this. MED 4, 3. So, that would be for exponential and poly. MED 4 would be just the first 4 letters of X, so expo, and then MED 3 here would be the first 3 letters of Y, would be pol. Okay, so you would we would have to get okay, so for the first one we will have 3, 3. So that would be X, EXP, and pol, right? So that would be EXP and POL. And the cost of this would be 3, right? So MED of 3 and 3, and then the plus 1 because of the plus 1 here. And then for the other one, MED of 4, 2. So this would be 4 and 2 would be EXPO and PO. Now, how would we align EXPO and PO? So probably the best way to align it would look something like this, right? So because this is 4 and then this is 2, right? So it only has a cost of 2, right? And then plus 1. Okay, and then finally for the last sub-problem, MED of 3, 2, so this would be 3 here and then 2. So EXP and PO, it would probably look like this, ang best possible alignment niya. So it has a cost of 3 as well, and then the plus 1. So which one is the minimum among the three? So we would actually choose this one because this is the minimum, which is just 3. Okay, so the best way to align expo and pol for now would be this one plus the middle one, wherein we align L with a blank. So that's why it has a cost of 3. Because if it was O with a blank, that would have been 4, right? If it was O with L here, that would have been 4 ang ano niya, difference. Okay, so that is how you find the subproblems. So for the tabulation, we will need to solve for smaller subproblems first, and we need to store the answers in an m by n table. Okay, so what are the smaller subproblems? Okay, so we've established that these three are smaller than MEDAB, right? So we need to solve this 3 first before MEDAB. And how it looks like in a table would be something like this. Okay. Okay, I'll show that later na lang. And basically what we can do is we can go per row from left to right, or we could also go from per column from top to bottom, but for this one we'll just go with option 1. So we'll go per row from left to right. Okay, and then the base case would be the smallest subproblems. That would be minimum edit distance of 0 with whatever, or minimum edit distance of whatever with 0. So minimum edit distance of 0 with B, that would be, what would that mean? Okay, so di ba ang sa MEDTA, this is A and B. So if A is 0, we are taking a 0 length prefix of A. That means it's an empty string. Okay? And we are taking a B length prefix of Y. So it's an empty string, a blank, versus Y1 up to YB. So what is the minimum edit distance of a blank string with a string of length B? So obviously that would be B as well, because you need to align all of them with blanks, right? So if it's minimum edit distance of 0 with B, that would be equal to B. Okay, now for minimum edit distance of A with 0, it would be the opposite naman. Okay, you're aligning an A length prefix of X with a 0 length prefix of Y. So that would be X1, X2 up to XA, and then nothing for Y. So that would all be blanks. Okay, so you're comparing it with an empty string of Y, so the cost of this would also be A, because you'll align everything with a blank. Okay, so that's how it will look like sa base case. So if we look at the table, for example, let's say color and cloud, this is the base case. We call this the gutter values because they're in the gutter, right? So this one will have 0, and then this one will have 1, because basically this means that it's an empty string. So empty and empty. So it's an empty string versus C. So edit of 1, right? Empty string versus CO. It's an edit of 2. Empty string versus COL. It's an edit of 3, and so on. And then for this one naman, we have empty string versus C. We have 1. Empty string versus CL. We have 2. Empty string versus CLO. We have 3, and so on. So that's why we can fill the base case values quite easily, because this is just 0 and then 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. So just increasing. Okay? So those are the base case values. Now, going back to the algorithm, so we can put all of them together now. Okay? So if M is the length of X, N is the length of Y, we'll initialize a table of size M by N. So this is the table. size m by n. And for a from 0 to m, we'll initialize a0 with a, and for b from 0 to n, 0b with b. So these are the base cases. So 0, 1, or no, this is 1, 0, 2, 0, 3, 0, 4, 0. So equal lang siya sa base case. Okay? And then this one as well. And then after that, we will go through the table per row, and then from left to right. So for A from 1 to M, for B from 1 to N, we will just get the med of AB. So we'll consult med of A minus 1B plus A minus 1B, AB minus 1, and A minus 1, B minus 1. Okay? And then the D here is the difference. So whether XA is equal to YB. Okay? Meaning, are they the same? If they're the same, then the cost is 0. Otherwise, it's 1. Okay? Because they are different, it has an substitution cost of 1. And then, after consulting the 3, we'll get the minimum, and we'll get the value for med of AB. And then after filling up the table, we'll just return the med of MN. So how will that look like? Okay, so for the table, it will look something like this. So let's say that this is AB. This is the coordinates for AB. Where is A minus 1B? So that is previous row, same column, right? Because it's A minus 1. So that is actually here. A minus 1, and then B. Okay? How about A, B minus 1? So it's same row, previous column. So it's actually here. A, B minus 1. Right? And then how about this one? A minus 1, B minus 1. So that's the previous row and previous column. So A minus 1, B minus 1. So it's across the diagonal. Upper left diagonal. So for the upper left, you'll always add plus 1 here because of the plus 1 here. And here, we'll also add plus 1 here because of the plus 1 here. But for this one, it could be plus 1 or plus 0, depending on whether they are the same, ang XA and YB. Okay? So, when you are looking at this entry here, you'll actually just need to consult the 3 neighbors. So, up, left, and the diagonal here. So, just consult those 3 values, and then you can easily decide which one is the minimum, and then you put the value here. Okay? So, like here for example, so after filling up the values for the gutter values, the base case values, we'll start with this portion here. So what is the minimum edit distance of C and C? So here and here. So you'll notice we highlighted the 3 neighbor sub problems because those are exactly the 3 sub problems that we'll be looking at. So the up and left will always have the plus 1, right? But the diagonal this time has a plus 0 because they are the same letter, C and C, right? So which one is the minimum? Well, it would also be 0, right? So we will choose 0 here, and that would be the value. Okay? And then for the next one, we're highlighting the next 3 sub-problems. So this one also has a plus 1, also has a plus 1. And this time, the diagonal also has a plus 1 because C and L this time are different, right? So since they are different letters, we will add an additional cost of 1. So this became 2, 3, and 1. Which one is the minimum? So it would be the 1 here. So we will copy that value and go to the next sub-problem. So that is how the table will progress. Okay, just look at the 3 neighbor cells, up, left, and diagonal. My plus 1 sa up and sa left always. Okay, and then the diagonal is dependent on whether the letters are the same. Okay, and then choose whichever is the minimum. Okay, so going back here, that is exactly what this is doing, no? So we'll go for each row, from left to right. Just choose the minimum between the three. So if you finish this row, for example, we'll go to the next one. Okay, so for this next row, we'll get this one, and this works because you always have the three values computed for you, right? Because the previous row is already done, so you'll always get the diagonal and the up, and the left one is also done because you've done that in the previous sub problem. So you always have the three sub problems available for you. Okay, so now if we analyze this algorithm, how long will this take? So this one will be constant, constant, constant. This one will take m steps, right? Because for 0 to m. This one will take n steps because from 0 to m. And then the outer loop will run from 1 to m, so that's also m. While the inner loop runs from 1 to n, so m times n siya. Okay? So, and inside, we're just looking for the minimum between or among three values. So this is just constant time, right? So we have the first loop is m, and then add the second loop, which is n, and then the third loop has an outer loop of m times the inner loop of n times O of 1 per iteration. So this is m plus n plus mn. So if this is the equation, this is just O of mn, because mn is the biggest power here. Okay, so that is the analysis for our Wagner-Fisher algorithm for minimum edit distance. Okay, so as I mentioned, m iterations ang first loop, second loop n iterations, outer loop m, inner loop n, so O of 1 time per iteration. So we have O of mn in total as the running time. Okay, so the running time of this algorithm is O of mn, and then the memory is also O of mn because we use an m by n table, this one, right? So you have an additional memory of m times n, where m again is the length of the first string and n is the length of the second string. Okay, so you save the computed data in the m by n table. That's why we have this memory consumption. However, we could actually improve the memory to O of n, because in reality, each iteration only checks the current and previous row, diba? So for this iteration, for example, we're only interested in this row and this row. So we don't need, when we're already in this row, we don't need about the rest anymore, right? So we could just save two rows, the previous and the current, and then n columns, so that would be O of n na lang. So we don't need to we don't need to save the full table. We just need to save the two previous rows if you want to improve the memory. Okay, but for our example here, we'll just save the whole table because it doesn't really matter that much in small examples anyway. Okay, now the algorithm that we discussed so far only solves for the minimum edit distance, so meaning the minimum cost. But what if we want to find the best alignment? Okay, like how do we align color and cloud? So if we finish this one, we'll find out that the minimum edit distance of this would be 3. But what is the alignment of color and cloud such that the edit distance of 3? So how will we find that out? So since we've been only saving values or numbers so far, we actually need to save additional information to create the best alignment. So we need to keep something called the backtrace. Okay? And if you've been paying attention to the example, we've actually been doing that. And these arrows are the backtrace, basically. And basically what we'll just do is you'll remember which entry won the minimum. So if it was the upper entry that won, then you'll add a direction up. If it was the left entry that won, choose the direction left, and then if it was diagonal, choose the direction diagonal. So if we reset this, so for example here, which one won the min? It was the 0, right? So we have a diagonal stored in the array or in the table. And then for this one, the winner is the left, right? So we store the left arrow. And then here we have the left also. Here we have the left also. Here left. Here up. Here diagonal, diagonal, left, left, up, diagonal, and so on. Now, if there are tiebreakers, in some cases there could be multiple minimum values. Like here, for example, it could be up or diagonal or left, right? But for our tiebreaker, let's just choose diagonal before up, before left. So diagonal first, okay, for tiebreakers. So we've been keeping track of the direction that won the min, which entry won the min. And these arrows will guide us later on in creating the best possible alignment. So for the base case of the arrows, all the gutter cells should point towards 0, 0. So up ang sa may first column, and then pa-left ang sa may first row. So if we reset this again, you'll notice that all of the arrows here in the gutter cells in the base case all point towards this cell, the 0, 0 cell. Okay, so up and then left. Okay, so that's the base case. So when you initialize from 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5 here, you also initialize the directions up and then left. Okay, so that's the base case. And then after we've done everything, so let's say we've fast forwarded everything and reached this part here, we will use these arrows to trace the path starting from the bottom right up to the top left corner, or the 0, 0. So we'll follow the directions, okay? And the directions will tell you the alignment. If it's up, it's a deletion. If it's left, if it's an insertion. And if it's diagonal, it's an alignment, okay? So you can also store more than one direction if it's tied, but in our case, we'll just choose the tiebreaker. So choose diagonal, up, and then left, okay? So any path from M to N to 0, 0 is a sequence alignment with minimum cost if there are multiple paths possible, okay? So let's see here the color versus cloud. So we'll start with the bottom left here, which is MN, and then we'll follow the direction. So since this is the diagonal, this is an alignment of R and D, and then we'll follow it here. So next is left. So left is an insertion of U, and then we'll go here because it goes to the left. So diagonal, it's alignment of O and O, then diagonal, alignment of L and L, then up, so it's a deletion of O, then diagonal, alignment of C and C, and then if we reach 0, 0, we are done. So if we follow these alignments here, this is now the final alignment of color and cloud that gives us the minimum edit distance of 3. Okay, so C and C are aligned, L and L, O and O, and then you have the 3 edits here, which gives us the edit distance of 3. Okay, so that's it. Now let me show you one more example, this time for hello and world. Okay, so for hello and world, again, we've initialized the base case values here. So 0 from 1 to 5, 0, 1 to 5, and then the arrows are pointing up and pointing to the left. Okay, so we start here. Since H and W are different, so everything has a +1. Okay, and then the min is the diagonal, so it's 1. For this one, also +1. So the minimum is diagonal. So since there is a tie, we'll prioritize the diagonal, so 2. And then for this one, it's also 3 diagonal. For this one, 4 diagonal, 5 diagonal, 2 diagonal, 2, 3 diagonal, 4, 5, 3, 3, 3. Now this time, it's the first time that we have the same letters, no, L and L. So you'll notice that only the left side and the upper side has a +1. The diagonal doesn't have a +1 because the cost of aligning L and L is 0 because they're the same. So the minimum here is 3, which is the diagonal. Okay, and then for the rest, you'll have that. And then L again has a +0 here because it's the same. Okay, and then for D. Okay, so now that we have solved the whole table, we will start the back trace. So from here, diagonal, 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 and we've reached the 0, 0. So this is the alignment of hello and world to get the minimum edit distance of 4. Okay, so there's only one possible alignment. Okay, so that's it. This is the back trace. This is the alignment. So that's it for part 1. So what we've discussed so far is for dynamic programming, we need overlapping subproblems, and the subproblems have an optimal substructure, meaning that they contribute to the optimal solution of the original problem. Okay, and then we will tabulate from doing the bottom-up approach. So starting from the base case, so fill those up first, and then for the bigger subproblems, we'll just consult the smaller subproblems since we've already saved their values. Okay, and then for minimum edit distance, the first problem that we discussed, we used the prefix of the two strings x and y, and we'll get the minimum of the 3. So a minus 1b plus 1, ab minus 1 plus 1, a minus 1 b minus 1, and then the diff of ab. So again, if it was on the table, it's quite simple. We just look at if you're here, you just look at this, and this cells. This one has a +1, this one has a +1, this one has a +0 or 1, depending on whether they are different or not. Okay, and then get the min of that, those 3 values. So that's it for part 1, and part 2 will follow shortly. Okay, so we are now in part 2 of our dynamic programming lecture, and we will discuss 2 more problems, namely the longest common subsequence and longest increasing subsequence, and see how dynamic programming is used to solve these 2 problems. But first, we need to find out what a subsequence is, okay? Because that's common to both problems. Now, subsequence is not this one, right? Sub-C-queens. It's not this one. But given 2 strings, x and y, x is a subsequence of y if you get x by dropping 0 or more elements of y, okay, while preserving the relative order of elements. So you delete 0 or more elements of y, but the order remains the same. Okay, you don't shuffle it, or you don't rearrange it. So in the subsequence, it's not necessarily contiguous or side by side like a substring. Okay, because in substring, it could look something like this, right? A, B, C, D, E, F. The substring could be like C, D, E because it has to be contiguous. For subsequence, it could be something like this. For A, B, C, D, E, F, like B, D, F is a subsequence because you get B, D, and F by removing these 3 letters while preserving the same order. Okay, so that's the difference between a substring and a subsequence. Okay, so let's see some examples. Is ABC a subsequence of ABCDE? Well, yes, because you can get ABC by removing D and E, right? How about BCD is a subsequence of ABCDE? Yes, because you can get BCD by removing this 2. Okay, how about this one? yes, this is also a subsequence because you can get ACE by removing B and D. Okay, so while preserving the relative order. And then finally, how about BAE? Is it a subsequence of ABCDE? Well, no, because even if you remove C and D, it has A, B, and E, but it's not in the correct order. So this is not a subsequence because it doesn't preserve the correct order. Okay, so that's subsequence. Now, how about common subsequence? So Z is a common subsequence from X and Y if Z is a subsequence of X and Z is also a subsequence of Y. So basically, Z is a subsequence of X and Y. So therefore, common subsequence siya. And so this is where we start with our first problem in part 2. So the longest common subsequence. Okay? So given that we understand already what a subsequence is and a common subsequence, we are now going to find the longest common subsequence, or LCS for short. So for our input, we're given two sequences, X and Y, with lengths M and N respectively. So take note of this notation because we'll be using this later. So X, the first one, has a length of M, while Y, the second one, has a length of N. Okay? And the output is the sequence Z of length P, which is the common subsequence of the two, X and Y, and it has the longest possible length. Okay, so it's the longest possible common subsequence of X and Y. Okay, so let's see an example. If X and Y were these two, A, B, C, D, E, and B, C, E, A, D, Q, what would be the common subsequences? So some common subsequences would be BCD, right? Because you have BCD there and you have BCD here. You also have AD, AD here, and then AD here. And then you also have BCE, BCE, and then BCE. So those are the common subsequences. But the longest one would be either BCD or BCE because that has length 3, right? This one, although it's a common subsequence, it's not the longest one. Okay? So that is the longest common subsequence problem. Now, why are we interested in this type of problem? Well, the length of the LCS between the two strings tells us about the similarity between the two strings, X and Y. So the longer the LCS length is, the longer the common subsequence is. That means that they're more similar, right? Because they have more things in common. So some applications of this include spell checkers, just like minimum edit distance, autocomplete, and even checking similarity of DNA sequences. So more or less similar siya with minimum edit distance, but sa edit distance kasi we are trying to align them in the best possible way and trying to find the minimum possible edits or substitutions, deletions, insertions. Here, we're just trying to find their common subsequence. Okay, what is the similarity between the two? Okay, so before we discuss the dynamic programming solution, let's try to look at the brute force way first. Okay, so how will the brute force algorithm work? So we have to try all possibilities, right? So first, we need to generate all subsequences of X and all subsequences of Y. And then we'll get the common subsequences, so the intersection between the two, and we'll return whichever is the longest common subsequence. Okay, so it seems pretty straightforward, but if you put all of that into an algorithm, it will look like this. So X subsequences would be all subsequences of X, all subsequences of Y would be this one, and then you'll have to look at all subsequences of X and Y together, so as a pair, and if they are equal, so that means that they are a common subsequence, and then this part is just trying to find the longest subsequence. So you're keeping track of the current max length, and if it exceeds the current max length, then you update the LCS and the max length itself. Okay, so you'll have to look at all pairs, right? So it seems pretty straightforward, but how many pairs are there in total? So let's try to analyze the algorithm. First, is it correct? Well, yes, it works because you're actually trying all possibilities. So you should be able to find the longest common subsequence. Does it run in reasonable time? Now, this is where we'll have a problem. Because if we check here, okay, let's try to analyze this one. How many subsequences of x are there? Subsequence of x. So, if that is, let's say we have a sequence of length 4. So, A, B, C, D. So, how many possible subsequences are there? Or maybe I'll even reduce this one to 3 na lang para shorter. So, how many possible subsequences are there? It could be just A, just B, just C. That is, those are valid subsequences. And then there's also AB, AC, and BC. And then there's also the subsequence ABC, which is you're not deleting anything. So in total, there are 1, 2, 3, 4, 5, 6, 7 in total, wherein you had n was equal to 3 and your total subsequences was 7. And you actually got 7 from 2 raised to 3 minus 1. This is 8 minus 1, this is 7. Okay, so if you have, let's say, 4, A, B, C, D, you'll expect that this will have 2 raised to 4 minus 1, which is 16 minus 1, 15 possible subsequences. So, if x has a length of m, then you will have 2 raised to m na subsequences. And then, if y's length is n, no, we'll have 2n possible subsequences. Okay? And then for this one, so this will run, the outer loop will run in 2m, the inner loop will run in 2 raised to n, because that is the total number of subsequences. So in total, the running time is, well, 2m plus 2n plus the loop here, which runs, the outer loop is 2m, times the inner loop 2n, and inside, this is just constant because this is just checking, this is just comparison, right? So O of 1. So in total, that would be 2m plus 2n plus 2mn, which is O of 2mn. Okay, so that is the total running time. So you are exponential in the running time, and it's not just even 2n, it's 2mn. Okay, so again, all subsequences of x is 2m, subsequences of y is 2n. The double for loop will have 2m times 2n, so 2m 2n or 2mn. So can we do better than this? Okay, yes, we can. We can improve the brute force version. So first, we can generate all subsequences of x, and then for each subsequence, check if that subsequence is also a subsequence of y. So we don't need to generate all subsequences of y this time. Just that if x, for all subsequence of x, check if it's also a subsequence of y. Okay, and then return the longest common subsequence. So we can improve it by just finding out all subsequences of x. Okay, but we have a new procedure, or a new function, is subsequence. Okay, so for is subsequence, it will look something like this. It will just check whether that z is a subsequence of y. Okay, so this one will just run in O of n. Okay, let me remove all of that. This will run in O of n, right? Because you have a loop from 1 to n. Okay, so that's the main loop, and then inside is just comparison. So is subsequence will run in O of n time. Okay, so if we put all of that together, again, all subsequences of x is 2 raised to m, right? So this will run in 2 raised to m, and then each time there is an O of n running time for this one. So all in all, 2m, and then the for loop has 2m iterations, and then each loop will also take O of n time to check if it's a subsequence of y, and 2m iterations times n, that would be n times 2m. So we have actually improved from the 2m n running time that we had earlier, right? But this one is still exponential, or even more than exponential, because you have the extra factor of n here. So can we do better than this? Well, we can, of course, right? So this time we will use dynamic programming, and for this one, which sub-problem pattern do you think should we use, given that we have two inputs? So of course we can't use prefix because it only has one, or substring, it only has one. So we'll have to use the pair of prefix because the LCS problem has two inputs. Okay, so we'll need to use pair of prefix. So the pair of prefixes of x and y, so we'll denote it again as x from 1 to a is the a length prefix of x. So that means that if it's, let's say, a, b, c, d, e, c, x, if you have x from 1 to 3, that just means a, b, c. So the first three letters of x. If it's x1 lang, then that's just a, right? And then for y, it's the same thing. Y from 1 to b is the b length prefix of y. And so after this, the first thing that we need to do is we need to characterize the structure of the optimal solution. Okay, so how will the optimal solution look like? So for the prefix x, we mentioned this already, no? X from 1 to a is the first a items of sequence x. So just like this, a, b, c, b is the first 4 items. And then if it's a zero length prefix, then it's an empty string because there is nothing that you're taking from the string itself. Okay, so if you see something like x0, that is only a zero length prefix, so it's an empty string. Okay, so we also need to find out whether this sub-problem follows the optimal substructure pattern. Okay, that means that does the pair of prefixes contribute to the problem, and does the problem itself help solve the pair of prefixes? So like for example, LCS of xy contains LCS of the subproblem from x to a, and then from y to b. Okay, so and the opposite of that is that the subproblems x1 to a and y1 to b contributes to building the original solution to LCS of xy. Now, what does all that mean? What does that all mean? So let's see, for example, this one, a, b, c, d, b, c, d, e, f. So what would be the longest common subsequence here? That would be b, c, d, right? Okay, now how about if we have a shorter or a smaller subproblem? So still a, b, c, d, but this time instead of b, c, d, e, f, b, c, d, e na lang siya. Okay, it would still be b, c, d here, right? And you'll see that BCD was still part of the solution sa bigger subproblem. Now, how about if we make it even smaller? How about if instead of ABCD, we remove the D here and it becomes ABC. So this is an even smaller subproblem than the previous one. This time, the LCS would be BC. But you'll see also that BC is contained in the solution to the bigger problem here. Okay, so that is what we mean by the optimal substructure. The solutions to the smaller problems contribute to the solution of the bigger problem. Okay, so it's part of the solution. Now, if we make this even smaller, we remove this one, it would still be BC, right? And that is also part of the bigger solution here, even. Right? So that is what we mean by optimal substructure. Okay? So now let's try to discuss further ang subproblems ng LCS. So we will have a notation LCS of AB LCS AB just means the LCS of the prefix x from 1 to A and y from 1 to B. Okay? So this is just a shortcut notation. And of course, our goal is eventually to get LCS of M and N, because remember that x's length is M and y's length is N, right? So that is our ultimate goal. And the next step is to express LCS AB in terms of smaller subproblems, just like what we did in minimum edit distance, right? We express this one in terms of smaller subproblems, and so that is now our step 2. Okay, recursively define the value of optimal solution. So that's what we'll do next. That will be our step 2. So given the two prefixes x to A and y to B, let's let Z from 1 to C be the LCS of these two prefixes. Now, how are they related? Okay, so x1, x2 up to x sub A, and then you have y1, y2 up to y sub B, and then their LCS is something called Z. So Z1 up to ZC. Okay, how are these three related? So the first case is if these two are equal, what does that mean for us? So like for example, if our test case or sorry, our prefix was ABC and just DC, for example, if they are equal, or maybe ADC, something like that. If they are equal, what does that mean for our LCS? So that means that this C is actually part of the LCS. So we will have this one as the last letter of our LCS, right? Because they are equal, they are common. So ZC would be equal to XA and YB because they are already equal, right? So this is also equal to that one. And what we will be left with after finding out that this is common would be to find out for the rest. So that would be from x1 up to xa minus 1 na lang because we're done with xa. So we are done with this. So we will only continue with this one up to a minus 1. And then for y, y1 up to y b minus 1 na lang because we're already done with yb. We've already found that they are common with xa, right? Okay, and we are only left with z from 1 to c minus 1 na lang because, well, you're already done with zc, right? So, and since that is a match, we will also add plus 1 to the LCS length. So, LCS plus 1 because there is a common letter, which was this 2. Okay? So, we'll add plus 1. That is if they are equal. Okay? But what if they are not equal? Okay. So, if they are not equal, okay. So, first, the first case is LCS of AB becomes LCS A minus 1, B minus 1 because we'll continue with this subproblems, and then plus 1 because of the match. Okay? So, that's the first one. So, we'll write that here. LCS A minus 1, B minus 1, plus 1. This is if XA equals YB. So, meaning the last letters are the same. Okay? But what if they're not the same? What will happen? Okay, so let's erase this first. Okay, so if they're not the same, we will have to go to case 2. So, the case 2 is something like this. So, x1, x2 up to xa, then y1, y2 up to yb. and then there's Z1 up to ZC. Now, if these two are not equal, okay, if they're not equal, then there's nothing common with them. And what if we know that ZC is not equal to the XA? If they're not equal, then if it's not this one, then we are left with X1 up to XA minus 1 na lang, because we are sure that we said that XA is not, it's not part of the LCS. And then we'll continue with Y1 up to YB, because we don't know, maybe YB is in common with the A minus 1, right? So we will continue with X to A minus 1 and then Y up to B. And then since there is no match, it's still the same LCS, so we won't add 1 unlike the previous case. Okay, so that that case would be this one. So if XA is not equal to YB, one option would be to get LCS of A minus 1 B. Okay, but there is another option as well. What if it was not equal to YB? Okay, so what do we mean by that? What if we are sure this time naman, what if we are sure that the last letter or the last element of the LCS is not YB? Okay, so if it's not this one, then we can continue with Y1, Y2 up to YB minus 1 na lang, because we are sure that YB is not part of the LCS. Okay, while for X, it would still be X1, X2 up to XA, because in this assumption, we're not assuming anything for X. Okay, we are only assuming that it's not equal to YB. That's why we removed YB. Okay, so in this case, we will continue with the sub-problem X from 1 to A and then Y from 1 to B minus 1. Okay, and since there's no match, these are not equal. Okay, they're not equal. It will also have the same LCS length, so no plus 1 as well. Okay, so that would be the sub-problem LCS of A B minus 1. Okay, so we now have two different cases. If XA is not the last letter of the common subsequence, and if YB is not the last letter of the common subsequence. So if we put all of that together, okay, we have the following. So if XA is equal to YB, we'll solve A minus 1, B minus 1, and then plus 1, right? If XA is not equal to YB, we solve the two sub-problems, A minus 1B and AB minus 1, right? And since we don't know which between the two would be longer, we'll solve both and get the max. Okay, because we're looking for the longest common subsequence, so we'll get the max between the two since we don't know. Okay, now hopefully by now you can see the overlapping sub-problems again. Okay, because if you imagine it in a box again, in a table, it would look similar to the minimum edit distance, right? If this is AB currently, A minus 1, B minus 1 would be this diagonal, right? Because it's A minus 1, so previous column, tapos B minus 1, previous row. A minus 1B would be the upper cell, okay? And then AB minus 1 would be this one, okay? So there are overlapping sub-problems because, for example, let's draw a table here. Okay, so let's say that you're looking at this one currently. So for the X currently, we are looking at this sub-problem, and this sub-problem. So we are using all three here, 1, 2, 3. And then if we move here, the ones that we'll be using are this one, and this one. So we've already seen a reuse or an overlap because this one has been used twice, this one has been used again. Okay, and then if we move on to the next row, for example, like here, the previous row would be now the upper cell, and then here, and then the diagonal. So we'll be reusing all of these sub problems again. So they are really overlapping. Okay, so that is the sub problem. Now, for the base case naman, we need to establish the base case, right? Because we cannot start populating the table if we don't have any values that start the table in the first place, right? So LCS of A0 is 0 and LCS of 0B is 0. Now, why is this the case? Because if it's LCS A0, that means that you're taking the A length prefix of X and the 0 length prefix of Y. So if you're comparing it with the 0 length prefix, it's an empty string. So the longest common subsequence between a string and an empty string is nothing because there's nothing to compare it with, right? So both of them are 0. So the gutter values later on would be 0. Okay? So if we look at this one here, so this is the input, for example, if we set up our table, the gutter values here would be all 0, right? Because what this means is that the LCS of empty string. So LCS of A and empty string is 0. LCS of AB and empty string is 0, and so on. So everything is 0 because you're comparing it with an empty string, right? So, okay. So that's the base case, and this is the final recurrence relation. So if it's the base case, if A is 0 or B is 0, then we write 0. If the two letters currently, X, A, and Y, B, are equal, then we look at the diagonal, right? Plus 1. And then if it's not equal, then we'll just compare the upper cell and the left cell and take the max. Okay, we won't add plus 1 because there's nothing in common anyway. So the way that would look like in the table would be like this, right? So AB, A minus 1, B minus 1, A minus 1B, A, B minus 1. So if it's equal, okay, we look at the diagonal, plus 1. Okay, but if it's not equal, we look at this two here and get the max. Okay, we're getting the max because we're interested in getting the longest possible common subsequence. So whichever of the two has the longer one, longer value or bigger value, then we will get that one as well. Okay, so that is the recurrence relation. So we are now ready to tabulate everything. So we'll compute the value of the optimal solution using the bottom-up approach. So we will use an m plus 1 by n plus 1 table. So basically an m by n, we just add 1 to both dimensions because of the gutter, the base case values. Okay, and we'll be following the row major order just like in minimum edit distance. So we're going per row and then go from left to right. Okay, so we will also be keeping track of the back trace just like what we did in minimum edit distance. So we'll also use a similar table, same size, and the direction for each cell points to the direction of the sub-problem that was used to compute the LCS of AB. So if you use the diagonal cell, then the direction is diagonal. If it's the upper cell or the left cell, then you point to that direction as well. Okay, so very similar to what we did in minimum edit distance. So putting all of that together in a algorithm, it would look something like this. So you have two tables of size m plus 1 by n plus 1, and then you will initialize the base case. So for LCS A0, all of that would be 0. For LCS 0B, all of that would be 0 as well. And then this one would be going through per row, so for row from 1 to m, and then this one is going from each column from left to right, so from 1 to n. We'll check if xa is equal to yb, then if they're equal, we check the diagonal, so a minus 1, b minus 1, and then plus 1, and then update the direction. Otherwise, if they're not equal, we need to check which one is bigger. Is it the cell above or the one on the left? And that's what we'll copy. So either up or left, depending on which one is bigger. Okay, and then after we've gone through the table, we will just return LCS MN, or the bottom right corner. Okay, the bottom right value. But again, this is only for the length of the LCS. Okay, if we need to get the actual subsequence itself, the longest common subsequence, that will come later. Okay, there's another separate procedure for that one. But for the analysis of this one, okay, let's try to analyze the algorithm here. So this one will run in m times steps, because this is from 0 to m. This will be in n times steps, 0 to n. The whole thing here, outer loop, runs in m, because that's from 1 to m. And then the inner for loop runs in n times steps, because it's from 1 to n. And then inside, it's just constant time, because it's just comparison, right? And saving of values. So that would be m times steps plus n plus m times n, because you have to multiply the two because of the double for loop. So that would be O of mn, ang running time niya. Okay, so that is the analysis for our LCS algorithm. So we're filling up two m plus 1 by n by 1 tables. Each entry takes O of 1 to compute, so the running time is O of mn. Okay, and the memory, of course, is also O of mn, because again, we are using two tables of size m by n, basically. Okay, now for the backtrace, remember that we are keeping track of the directions so far. So what we'll do is, we'll start at the bottom right corner, or the mn na coordinates, and then while the current is not null, so while it's not blank, we will just follow the direction. Okay, and if it's diagonal, then we'll move diagonally. If it's up, then we'll move one row up. If it's left, we'll move one cell to the left, and then we'll just follow that one. And then whenever we encounter diagonals, that means that it's common, diba? Because earlier it would be common if it's here, right? If it's diagonal, it's equal ang xa and yb. So every time we encounter the diagonal, we take note of the letter currently, and then we'll add that to the LCS. But since we started from the bottom going to the top, we will reverse the LCS that we have found. Okay, so we'll see that in an example later. So this is how we'll construct the optimal solution. So start at bottom right, follow the directions until there is no more direction to follow, and then once we encounter the diagonal, that is part of the LCS. Okay, and then we'll reverse the letters that we've found. Okay, so this one will take basically, you're moving one row or one column at least per iteration, right? Because going back here, if it's a diagonal, you're moving both one row down and one column down, right? If it's up, it's just the row going back, and then if it's left, it's just the column going back. But each iteration, either one row or one column is decremented, right? So the worst case is it would take m plus n time. Okay, because this one is all the rows and all the columns. Okay, so m plus n lang ang time for the backtrace to take. So let's now look at the example that we have here. So so we've already filled up the base case values. The gutter values are all 0, and you'll notice that there are also no directions for the gutter values, because we'll just keep them null. So once you encounter a gutter value here, then we'll stop, okay, in the backtrace later. So we'll start here. A and B are not equal, so we'll be looking at the upper and the left. And for the tiebreaker, we'll just prioritize the up here. And it's just a simple comparison of whichever is the max. We won't add anything, right? Because they're not common anyway. So it's max of 0 and then up. And then here, it's also not equal. So max of 0, up. This one is also not equal, so 0, up. But this time, A and A are equal, right? So this is common. So we'll need we'll look at the diagonal and then add 1 to that one. So plus 1, so the max is 1. And then the direction is diagonal. And for this one, this time the max is now the left, right, with 1. And then for this one, left also. Sorry. For this one, it was equal, by the way. So A and A. So we check the diagonal and then plus 1. So it's 1 diagonal. And then for the next row, B are also the same. So we'll check the diagonal. That's 1. It's not the same. So it's 1 left. Not the same. 1 left. Not the same. 1 up. Because in this one, we're prioritizing the up over left. If it's the same B, so 1 plus 1 is 2 diagonal. Here, the max is 2, right? So we're not adding anything. Here, the max is 1. Max of 1 up. Same, so 1 plus 1, 2. Different, so max 2. Here, max 2. Max 2. The same again, so 0 plus 1 is 1. And this will just continue, okay, doing the same pattern. Just remember that if they're not the same letters, we need to look at the upper cell and the left cell and get whichever is max, okay? But if they're the same, like here, we'll just look at the diagonal and add 1 to it, so it becomes 2, okay? And then keep track of the winning cell direction. So if we fast forward this to the end, and by the way, this is part of the demo videos for dynamic programming, so you can watch this again in slow-mo this time. And you can even pause whenever if it's going too fast. So this time we have reached the end, right? So it's the LCS 4. The LCS length is 4 between these two strings. But what is the actual common subsequence? So we will now do the back trace. So we'll start here at the bottom right corner. So up, so we'll go up to this one, and now we've encountered the diagonal. And remember that when we encounter a diagonal, that's a common letter. So we have A currently, and then we'll go here, so go up, diagonal, so another diagonal, so we'll take note of the letter again, it's B this time. Then we'll go here, left, diagonal, and then take note of the common letter C, left, diagonal, so common letter B. And then we have reached an empty space, so we will stop now. So this is the final path of the back trace, and we have found the common subsequence, the LCS of BCBA with the length of 4. Okay, so that is how you do the longest common subsequence using dynamic programming. Okay, so now this time let's take a look at the second problem in part 2, which is about longest increasing subsequence. But before we talk about the longest increasing subsequence, let's define what an increasing subsequence is first, okay? So an increasing subsequence is a subsequence where the numbers are strictly increasing. So it's simple as that, actually. So in here, if this is our example sequence, the increasing subsequences are 2, 3, 4, because this is in increasing order, 2, 3, 8, 2, 3, 7, 2, 3, 7, 8, and 2, 5, 7, 8. Okay, so there's a lot of subsequences here, right? So other subsequences could be like 2, 5, 3, or 2, 5, 4, something like that, or 2, 7, 4. These are also subsequences, but they are not increasing subsequences, because there is an increase here, but it decreased going back, right? So these are not increasing subsequences. So they are subsequences again, wherein the numbers are strictly increasing. So it's going up, 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 and up. Okay, so that is the increasing subsequence. So for the longest increasing subsequence, you can imagine that you're just trying to look for the increasing subsequence of longest possible length. Okay, so for this one, halimbawa, the longest possible increasing subsequence is 2369. Okay, 2369 with length 4. Okay, are there other possible, pwede man siya na 2367. Okay, that's also another LIS with length 4, but the longest possible length is still just 4. There is no other increasing subsequence with length 5 in this one, in this example. Okay, so let's try to define the problem formally. So for longest increasing subsequence, we'll get a sequence A of length n as our input. So we'll only have one sequence, okay? And it's usually numbers, but it can also be letters, okay? If it's letters, then just follow the alphabetical order. And our output is the LIS of A, so the longest increasing subsequence of sequence A. So it's LIS of A, not Lisa of Blackpink, okay? So LIS A pagbasa. Okay, anyway, so before we discuss the dynamic programming solution, let's again take a look at the possible brute force approach. Okay, so for the brute force, what we'll need to do is we need to find all subsequences of A first, right? And we'll only consider those that are increasing subsequences. So we'll filter out those that are not increasing. And then we'll return whichever increasing subsequence has max length. So seems pretty straightforward, right? So if we put that in a pseudocode, it would look something like this. So all subsequences of A, and then the max length is 0, and then check if that subsequence is increasing. So we need to do that for all possible subsequence. And this part is keeping track of the longest increasing subsequence. So keep track of the max length that you've found so far. If its length is bigger than the max length, then update lang. Okay? So finding all increasing subsequences takes O of 2n. Why is that? Because all subsequences of A, so if A has length n, subsequences for A will be, there are 2n in total, right? Remember in the earlier examples sa LCS, right? Because you could have, for example, for ABC, the subsequences could be A, B, C, AB, AC, BC, ABC itself. So that's 2 cubed minus 1. So where n is 3 here, that's 2n minus 1. So in general, it's about 2n. So you'll have 2n possible subsequences. So this loop will run in 2 raised to n. And then you need to check if each subsequence is increasing. So to check if it's increasing, that will actually take O of n na running time, because you will have to, the maximum length of the subsequence is n as well. What if you have the full sequence itself, right? So it will take the whole string to check. So the whole loop will take n times 2n, because you have 2n na outer loop and then n work at each iteration. So it's pretty bad because you have more than exponential time for the brute force. Okay, so can we do better? Well, obviously we can. So before we discuss the solution to the LIS, you can actually solve the LIS using the LCS solution. So how will you do that? So you can solve LIS using LCS by sorting the sequence itself, and you name that B, and then this will take O of n log n time if you use merge sort, and then LIS of A can be reduced to LCS of AB. Okay, why is that? Because, for example, if your LIS of, let's say, 1, 3, 5, 6, 8, 2, something like this, 1, 3, 5, 6, 8, 2. So we know that the LIS of this would be 1, 3, 5, 6, 8. So 5, right? Length niya is 5. But if you take the sorted version of this, it would be 1, 2, 3, 5, 6, 8. And then you get the LCS of the 2. You can actually get the same answer. So you'll get 1, 3, 5, 6, 8 here, and 1, 3, 5, 6, 8 here. So that is their longest common subsequence. So you can do it like this if you want to, but there is another way for you to solve the LIS without using LCS. Okay, so yeah, it will take O of n squared time. So let's now discuss the dynamic programming solution to LIS, but first we need to characterize the sub-problems itself. Okay, so let's say the LIS for 17236, what would that be? So that would be 1236, right? So it could be 1236 right here. How about if it's just 1723? That would be 123 ang LIS niya. So 1 and then 2, 3. Now, how about if it's just 172? Then it could be 1, 2 or 1, 7. But do you notice that this looks like optimal substructure? Because this one is 1723 is a smaller version of the 17236 problem, because we just omitted 6 here. And the solution for this one contains the solution for this one, right? So 1, 2, 3 can be found in the solution here when we just drop this one. And then when we drop 3, the solution for the smaller subproblem 172, which is 1, 2, was also contained in the solution to the previous bigger subproblem. So that looks like optimal substructure, right? The solution of the smaller problems contribute to the solution of the bigger problems. So the LIS of the shorter sequence is part of the LIS of the longer sequence. So this is what I mentioned earlier. So for the subproblem, we will use the prefix pattern as the subproblem. So we'll start from 1 up to some value A. Okay, so we will denote LIS of X to be the LIS of the prefix from 1 to X, because again, take note, the A has length from 1 to N. So X could take on the values from 1 to N. Okay, so the goal eventually is to get the LIS of N, which is the LIS of the full string with length N. Okay, so for the recurrence relation, this is the full recurrence relation, and let's try to discuss what we mean by this. So for the recurrence relations, we're currently looking at LIS of X. Okay, so where will we look at for previous subproblems? We will look at previous sizes or previous indices from 1 up to X minus 1. So let's say if it was LIS of 4, so this time X is equal to 4, previous would be from 1, 2, and 3. Okay, so everything before current X. So for all previous values, okay, we have to make sure we only need to look at increasing numbers. So for these are indices, right? Index, yeah. So let's say A, or not A. Okay, sige, A, D, B, E, uh, maybe not D. A, D, F, E. Okay, so maybe let's try this one. So if x is equal to 4 now, this is our current x. So the previous would be this 3. 1, 2, and 3. 1, 2, and 3. So we'll only look at those previous items that are increasing with E. So does A pass that one? So AE is increasing, so we will get this one. DE is also valid because D to E is also increasing, so this is good as well. But FE will not be included because it's not increasing, so it will not be part of an increasing subsequence, right? So we will skip this previous item. So we'll only look at previous items that are also increasing with the current item that we're looking at. Okay, so this is what it means by this part here. So dapat increasing siya. And then whatever is the current LIS of those previous values, because presumably we have solved those LIS from the previous iterations, whichever is the max and then plus 1, so we will choose that one. So maybe if this has a value of 1 or 1, and then this has 1 as well, so between the two, sino ang, or sorry, this one will have 1, this one will have 2 this time, and then this one will have 2 as well. So where did we get those values? So A, D, F, and E. So LIS of 1. So for A, since isa lang siya, 1 lang siya. For AD, that would be the current longest if it's only up to here. If it's AD and F, that would be actually 3, because this could be a whole increasing subsequence. And then if we're now looking at E currently, since we did not include this one, we will just look at this 2, A and D, and then we'll add 1 to each one, so this would be 2 and 3, and get the max. So actually it would be 3 here also. Okay, so why did we add 1? And that is because we are adding a new item to the subsequence, because since increasing siya, it could be added to the end of this sequence. So we're adding plus 1 here, and we'll get whichever is the max, because of course we're looking for the longest. Okay, so that is the explanation for this recurrence relation, but this will be better understood in the example later on, okay, when I show you the demo. So putting all of that together in pseudocode, so we will just initialize an array of length n. We'll initialize that with all ones for LIS value. Now, why is it all ones at first? Okay, because for example, say A, B, C, D. So current LIS nila would be initialized to 1, because since we haven't figured out the sequences yet, all of them are standalone, the longest increasing subsequence, because A could be a subsequence, B itself could be a subsequence, C and D are also subsequences. So currently they're only by themselves, so singleton sila na subsequence, and then later on as we go through, we will improve these values. Okay, so we will go through 1 up to the n, so going from left to right, and then we'll look at the preview, so again from 1 up to current minus 1, and then if it's increasing, then we'll check whichever LIS previous improves the current LIS current, and if it does, then we will update it, and then we will save a backtrace, which is the previous backtrace. So whichever index gave you this current answer, we will save that as the backtrace. Okay, that's what we mean by previous here. And then after that, we will just get the maximum LIS value that we'll find here. Okay, so I'll show you this how this works in an example later, but basically for the analysis, iteration 1 doesn't have a previous, so there's no previous. For iteration 2, you have one previous lang. For iteration 3, the previous would be 1, 2. For 4, that would be 1, 2, 3. And then for iteration n, that would be 1 up to n minus 1. So the total iterations would be 1 plus 2 plus 3 up to n minus 1. So this is the sum of arithmetic series, which we know is O of n squared, right? So the running time of this algorithm is O of n squared, and since we're using one-dimensional arrays of length n, the memory is O of n as well. So it's not mn or n squared, unlike the previous examples. It's only a one-dimensional array, so it's only O of n. Okay, so before we discuss the backtrace, let's take a look at the example first. So we have this one. So 291564338. Okay, so this is the input that we have, 291564338. This is the index, so from 0 to 7, and we initialized the LIS values to all ones first. Okay, and then the previous are all null for now. So that is the how we start. Okay, so we'll start at index 0. Well, it doesn't have any previous because it's the first one, so as is lang siya. And then next we'll go to current index is index 1. So it has one previous, which is 0. And let's look at this one. Will its LIS improve the current LIS? Well, it can, because if you add 1 to this one, it becomes 2, so it becomes better, right? And this is also valid because it's increasing. So 2 and 9, that is increasing, right? So we will consider this one. And since this will improve if we add 1 to it, because remember that it's LIS previous plus 1, so this will be updated to 2, and the previous would be index 0 because that was what we used for this value. Okay, so this LIS was the value here, LIS 1 plus 1. So from here, and then we add 1, it becomes 2. And then the previous is just the index that we used currently. So index 0. Okay? Now, we go to the next index. So since we're done with 1, we'll go to 2. And then ang previous niya starts at 0. But for this one, we will not consider this because 2, 1 is not increasing. So we'll skip that. How about 9, 1? This is also not increasing, right? So we'll also skip this one. So we'll go to the next index, which is now 3. So we'll start at previous 0 again. So this one is increasing, right? 2, 5. So let's check if it improves. 1 can be the 1 here can be improved if you add 1 to it, so becomes 2. Okay, so this is updated to 2, and the previous is now updated to 0, the current index here sa previous. And then let's go to the next previous, which is 1. So sa 9 and 5, this is not increasing, so we'll skip. 1 and 5 is increasing, but this will not increase or not improve the current LIS, because even if you add 1 to this one, it will still be 2, so it will remain the same. So since it cannot improve, then we will just keep it as is. Okay, now go to the next index, 4. Start at previous 0. This is increasing, so it's 2, 6, right? So, and then this can improve because if we add 1 here, it becomes 2. So this gets updated to 2, and the previous is 0. And then the next previous is 9, 6. So this is not increasing, but 1, 6 is increasing. So we'll check this one, but we cannot improve this further because it's already 1 plus 1, it's 2, and this is already 2, so it's just gonna stay the same, right? So let's go to the next previous, which is at index 3. So 5, 6 is increasing, so we'll consider this, and this one will actually also improve, right? Because this one will become 3 if we add 1 to it. So this time, the value becomes 3, and the index is also updated to the current previous, which is 3. Okay? So that is how we updated the previous here. And then now we'll go to index 5. This is increasing, right? 2, 4. 1, 1 will be improved, so we'll update that. This one is not increasing. This one is increasing but cannot improve, so we'll skip. not increasing, so we'll skip. Also not increasing, so we'll skip. Go to index 6. 2, 3 is increasing. We can improve the LIS, so we'll improve that one. It becomes 2. Previous 0. Not increasing. Increasing but cannot improve. Not increasing, not increasing, not increasing. So we'll skip. Okay? And then finally, sa last na index, so 2, 8 is increasing. So this becomes updated to 2, previous 0. Not increasing, increasing but cannot improve. Increasing and can improve because 2 plus 1 becomes 3. So this time 3 siya and the previous is 3. And then 6, 8 is also increasing and it can also improve because this one will become 4, right? If we add 1. So 4 plus 4, 4 and then previous of 4. And then this one is increasing but cannot improve, increasing but cannot improve. So we are now done. And we'll look for the max here, max LIS, and we find that at index 7. So we know that the longest increasing subsequence has a length of 7. Okay? So that is how we got the maximum length. Now for the backtrace, let's go back to this one. For the backtrace, remember that we have keep track of the previous indices. Okay, so for the backtrace, we'll just follow the previous indices. So we'll get the maximum of the LIS and we'll get the current count, current index of that max count, and then while it's not null, we'll follow the previous, go to the previous, and then add that number to the LIS. Okay, and then we'll reverse it because we're starting from the back. Okay, so find the max LIS, follow previous until no more next, and then reverse it because it's backwards. Okay, so at the worst case, it will take O of n running time because you're just going through the length n array at most once. Okay, so let's see, how will we go about the backtrace? So starting at this index, so we'll get the input 8, right? And then 4 ang previous index niya, so we'll go to index 4. So we'll get 6. Okay, and then we'll follow the previous niya, which is 3, so we'll go to 3. So we'll get 5, and then previous niya is 0, so we'll go to 0, get 2, and then previous is null, so we stop. And so we have gotten the LIS, which is 2, 5, 6, 8 of length 4. Okay, so that is the example. And then let's see one more example before we go, or before we finish this video. But I won't be narrating it in detail. Just follow along and pause if you have if it's going too fast. So we start at index 0. Okay, index 1, it's not increasing. Index 2, we can improve. Index 2, increasing but cannot improve. Okay, so can improve, cannot improve, not increasing, not increasing, increasing and can improve, so we'll update. Not increasing, not increasing. Here we can improve this one. We cannot improve, not increasing, not increasing, and then we can improve this one. So the value is now 3 and the previous is index 4. Index 6, we have this one. Cannot improve, we can improve, cannot improve, and then this can also improve, so it becomes 4, and the previous is index 5. And then finally at the last index, so this can improve, this will not improve, not increasing, this will improve, so it becomes 3, 3, and then not improve, this one will improve, so it becomes 4, 5, and then not improve. So we have now found our max LIS, which is at index the max LIS is 4 at index 6. So I just chose as a tiebreaker whichever came first. Okay, so let's do the backtrace. So current index, and then go to previous, which is 5, then previous, which is 4, previous, which is 1, and then null. So we'll stop here. So the longest increasing subsequence is 2, 3, 6, 9 with length of 4 for this one. Okay, so that is it for longest increasing subsequence. Now, would divide and conquer have worked for longest increasing subsequence or recursion? Would it have worked as well? If you use divide and conquer, it would have been a bad idea because there's a lot of the same sub-problems that gets solved repeatedly. Okay, so for example, since we're looking at the previous, diba? So for example, for LIS of 4, we'll be looking at LIS of 1, LIS of 2, LIS of 3 as the previous, right? And then for LIS of 2, we'll be looking at LIS of 1 as the previous. For LIS of 3, LIS of 1, LIS of 2. So there's a lot of the same sub-problems that get solved repeatedly. So it's really bad if you use recursion because there's a lot of repetition. Okay, so there's a lot of repetition. You get what I mean? Anyway, so why did recursion work well with divide and conquer? The key point was that the problem was divided into sub-problems that were substantially smaller, like half the size or like 1/4 or whatever, right? So gina-divide ta ang size. So there was a big drop in the problem size which made the recursion tree small. Okay? So in the divide and conquer recursion tree, we only have logarithmic depth, right? Diba log n lang ang length or the height of our recursion tree. And there would be a polynomial number of nodes if that is the case. So it's not too many nodes in the recursion tree. So it's only polynomial. And this is because the nodes are distinct. Okay? They are independent subproblems. So that's why it works well. But in the dynamic programming paradigm, the problem is being converted into sub-problems that are only slightly smaller, right? It's not divided by half. You're only reducing it by a small amount. Like for example, sa LCS of AB, it relies on LCS of A minus 1, B minus 1, or AB minus 1, or A minus 1B. So you're actually only reducing the size of the two inputs by at most 1 at each sub-problem. So it's not by a lot ang difference. Okay, and then for LISX, you have x minus k, wherein k runs from 1 to x. So it's also not a big difference in the size. Okay, and if the recursion is used for dynamic programming type of problems, the recursion tree will have polynomial depth and exponential number of nodes. So compare that with divide and conquer. Okay, so sa divide and conquer, okay, let's write that here. In divide and conquer, ang depth mo is only logarithmic. And the number of nodes would be polynomial. So O of n squared. Right? And then sa dynamic programming, the depth could be polynomial in depth. So O of could be n squared or n cubed. And then the number of nodes would be exponential. So it's going to be really bad because you go from polynomial to exponential in the number of nodes. Okay? And this is because most of the nodes there are repeating anyway. Okay? So there's too many sub-problems that you are solving again and again. Okay? So for dynamic programming, the efficiency is obtained by explicitly enumerating the distinct sub-problems and solving the sub-problems in the right order. So that if you solve them in the right order, solving the bigger sub-problems would actually be easier because you'll just be basing your answers from the previous answers as well. Okay, so just look at the three, let's say, surrounding cells and find the max or find the min. So it's just easy to compute because you have already found out the answers to the previous sub-problems. Okay, so that is how it gets its efficiency. You arrange the sub-problems in the correct order and solve them in that proper order so that it's easier to compute. Okay, so this is where we'll end part 2 of dynamic programming for now. So to review, we discussed the longest common subsequence problem, and it has the following recurrence relation. So for the base case, it's just LCS of AB is 0, and then if it's the same, you look at the diagonal. If it's not the same, you look at the upper cell and the left cell and get whichever is the max. Okay, and then for longest increasing subsequence, for LS of x, you look at the previous from 1 to x minus 1, consider only if it's increasing ang sequence, and then get whichever has the max LAS previous plus 1. Okay, so that is where we'll end part 2, and part 3 will begin in a short while. And yeah, but again, as I mentioned, it's best to watch or study part 1 and part 2 in 1 week, and then ang part 3, it could be next week na, because it would be too much to cram it in 1 week. Okay, so part 3 is coming up next.
Okay, so we are now in part 3 of our dynamic programming lecture, and this time we will discuss 2 versions of the knapsack problem, the unbounded knapsack and the 0-1 knapsack problem. But first, let's introduce the knapsack problem. So let's say, for example, there is a robber or a burglar who wants to like rob a place with valuable items, and the robber has a knapsack or a bag with a fixed capacity. So let's say the bag can hold up to 15 kilos, and then the items that he wants to steal has a weight also, so 12 kilos, 1 kilo, and so on, and they also have a value. Okay, so they each have their own weight and their value. So the knapsack problem essentially asks what is the best possible combination of items that he could take that could fit in his bag, okay, and that will also maximize the total value, okay, of the items that he took. So that is basically the knapsack problem. So formally, we will define the knapsack problem as follows. So for the input, we will get the knapsack capacity W. So this is the weight, total weight the knapsack can accommodate. Okay, and then there are n types of items where each item has a weight and a value. So one item could have its own weight and its own value. Okay, and the output is a combination of items such that the total weight of the items that we chose fits the capacity of the knapsack, and we want to maximize the total value as much as possible. Okay, so if we add up the value of the individual items, it is the maximum possible value. Okay, so that is the knapsack problem. And as I mentioned, there are several versions of the knapsack problem. There are 4 versions, but for this lecture we'll focus on these 2, unbounded and 0-1. But let's look at what they mean, okay, what the different versions mean. So in unbounded knapsack, each item has infinite supply. So that means that there is an unlimited amount of each type of item. So it's unbounded, okay, unlimited supply. Whereas in bounded knapsack, each item I has a specified supply, okay, so it has a finite count. So there is a number of copies per item. So let's say item A could have 5 copies, item B could have just 3, item C could only have 1, and so on. Okay, so like an unbounded, wherein it's infinite supply. Now for 0-1, this is a more specific version of bounded knapsack, wherein each item only has 1 supply. So there's only one there's only 1 count for each type of item. Okay, so you either take the item or not. Okay, so that is the decision you have to make. That's why it's 0-1, because if you don't take it, that's 0 of the item. If you take it, then you take 1 of the item. Okay, and then for fractional, it's similar to 0-1, wherein each item also has a supply of 1. So there's only 1 piece per item, and you either take the item or not, but since it's fractional, you could also take a fraction or part of the item. Okay, so let's say for example, if it's a gold bar, then that has to be 0, 1 because you either have to take the gold bar or not, right? But if it's like a chocolate bar, you could take the whole chocolate bar, or you could break the chocolate bar if it doesn't fit anymore, right? So you could at least take a portion of the item. Okay, so the fractional knapsack version, we will revisit this later in the greedy algorithms lecture. Okay, but for now, we'll focus on unbounded and 0, 1. Okay, so let's see an example scenario wherein the knapsack capacity is 10 kilograms and there are 4 types of items, A, B, C, D, with their respective weights and their values. Okay, so if it was unbounded, what would be a solution if it was unbounded? Okay, if it's unbounded, what are the possible solutions wherein you could reach 10 kilograms and have the maximum value? Now, if you only take A, that is allowed, so you'll only have 6 kilos. You still have 4 kilos left, but if you choose to only take A, that's fine as well. But you only have a total value of 30. Now, is this maximum? Probably not, right? So, how about if we add A and C, right? What if it's A and C? Because if it's A and C, that would be 6 plus 4, then it would fit the 10 kilo limit, right? It still fits the capacity. And their total value would be 30 plus 16, that would be 46. But is this the maximum? Well, let's see. Now, let's try other things. How about if we have 2 B's, so B, so that would be 6 kilos, and then add the C again, right? So that would be 3 plus 3 plus 4, so that would be 10 kilos as well, and the total value would be 14 times 2, so that's 28, plus 16 would be only 44. So it's actually worse than the previous combination. So maybe not this one. How about if it was 2 B's and 2 D's this time, right? So if you have 2 B's, that would be 6 kilos. If 2 D's, you get 4 kilos additional, so that would also be 10 kilograms in total, right? And the total value would be 28 plus 18, because there would be two items of B and D respectively. So 28 plus 18 would be also 46, right? So it's just the same with AC. Now, how about if we choose A and then 2 D's this time? Would that would still fit, right? Because 6 kilos plus 2 of D would be 4 kilos, so that's 10 kilograms. That's fine. And the total value would be 30 plus 2 times 9, or 18, so that would be 48. So this is actually the best possible combination. Okay, and that is if it is unbounded. So we could take multiple copies of D this time because it is an unbounded supply, right? So that's ADD. But what if we are following the 0-1 version, wherein you either have you only have one supply per item? So if it's only one supply per item, it could be, let's say, AC again. This would still be 10 kilos and the value would still be 46, right? Just like in here. If it's A and B, you only have 9 kilos, which is fine. You're leaving space in the knapsack, but if that's what you want, then it's possible. And you only have the total value of 30 plus 14, so this is only 44, right? So as much as possible, try to maximize the capacity.
to its full extent, right? Now, can we do BCD? What if we do BCD? So that would be 4 plus 3, 7 plus 2 is 9 kilograms as well. So that still fits. And then the total value would be 14 plus 16, this is 30 plus 9, it's only 39. So it's not the maximum. So the maximum actually is already AC. This is the best possible value that you could have, given that it's the 0-1 version. So if there's only one supply per item, then the best that you could do would be taking A and item C for a total value of 46. Okay? You cannot do something like ADD anymore because there's only one item of type D this time. So you cannot repeat D this time. Okay? So that is our example. So for unbounded, we have the maximum value of 48 with ADD, and for 0-1, it's only 46 with A and C. Okay? So the knapsack problem is actually a combinatorial optimization problem, and like to have like a short introduction for combinatorial optimization problems, you're trying to get like the solution for combinatorial optimization problems is usually a combination of items that optimizes the sum value. Okay, so these are usually hard problems because you're talking about combination of items, right? And if there's a combination of items, there's usually a lot of possible solutions. Okay, now there are two versions of the problem. There's the decision version and the optimization version. In the decision version, you're just asking, is there a solution where the total value is greater than or at least this type of value? So like, is there a solution that will get me at least 1,000 pesos or something like that? Okay, you're not asking if that's the best possible value, you're just asking if it's possible to have a solution that's at least this value. Okay, so that's the decision version. And then of course the optimization version is where you ask what is the maximum total value possible. Okay, the decision version of the problem is already NP complete, and if you're familiar with NP problems, the P versus NP problem, NP complete problems are basically hard problems in computer science, wherein taking or using brute force will take of course exponential time, and or at least exponential time. It could be more than that. And so far, there aren't any known polynomial time algorithms so far, right? So they're really hard because the best that you can do now is just brute force for general versions. Of course, there could be like polynomial time algorithms for small versions of the problem, but only if it's like a really small test case. If it's a big test case already, it might not work. Okay, so it's only for like limited scenarios. The optimization version of the knapsack problem is even harder, so it's NP hard. So NP hard problems are harder than NP complete problems. So later on, if we have time in during the semester, we'll try to discuss P versus NP problems as well. Okay, if we have time. So if the optimization and the decision versions are NP problems that so far cannot be solved in polynomial time, then why are we talking about it in the dynamic programming setting? The dynamic programming algorithm that we'll discuss will only work for small versions of the problem. It will not work for big test cases wherein you have a big capacity or a weight capacity, right? Or you have a lot of items. So the knapsack the knapsack dynamic programming algorithm takes O of nW time. So more or less this is still in polynomial time, and this will be reasonable time if W is small. But if W is big, then this will not be as small. Okay. So let's take a look at Unbounded Knapsack version first. Okay. Okay. So for the brute force approach, how will we brute force the unbounded knapsack? So of course, we can just repeatedly take item X because it has infinite supply, and the maximum possible number of takes that we could do is capacity divided by min weight. So for example, if we have like capacity of 10, right, and we have, let's say, 3 items, A, B, and C, and then this one has 2 kilos, 3 kilos, and 4 kilos. How many times could we take each item? Now, what's the maximum number of takes that we could do? So that would be the capacity, which is 10, divided by the minimum weight, which is 2 kilograms in this case, minimum weight of the items. So we could do up to 5 takes, right? Because that would mean that we could take A from 1 to 5 times, right? Because if we take A 5 times, it would reach the maximum of 10. Okay. For C, of course, it would take lesser because we could only take C up to 2 times, right? Because if we take it 3 times, it would already reach 12 kilos, which is above the capacity. And for B, we can only do it 3 times as well, because 3 times B would give us 9 kilos. If we take it 4 times, it would reach 12 kilos as well, which is not possible. Okay. And we will do combinations with repetition, wherein you take from 1 up to max take. And if you remember from your ComSci 57, right, this is the number of times that you would do for combinations with repetition, right? Remember, n plus r minus 1 taken r times, you have this equation wherein it's in factorial. So if it's in factorial order, then that means that it's really bad, because it's even worse than polynomial. Oh, sorry, it's even worse than exponential. So if we take all possible combinations, that would take too many combinations, right? But if we try to do that, then we will reject the combinations that don't fit the knapsack. So the combination of items that exceed the capacity, and then we'll just return the combination with maximum value. So seems easy enough, but the problem here is that there are just way too many possible combinations. Okay, so can we do better? Well, if we can't, what's the point of this lecture, right? So of course we can do better than this. So for the dynamic programming solution, remember that we have to formulate the sub-problems. So what would be the sub-problem for the unbounded knapsack version? So for the smaller problem, or the sub-problems, we will try to look at the smaller knapsack capacity. So let's say if the original knapsack capacity was 10, we'll try to look at smaller problems, like what if it was only 9, or if it was only 8 or 7, and so on, until we reach the smallest possible capacity. Okay, so those will be our smaller sub-problems. So we will have this notation K of W, small w. This is the maximum value achievable if the knapsack capacity is this small w, wherein the small w will range from 0 up to the actual knapsack capacity. Okay, the original knapsack capacity. Okay, so again, K of W will mean this is the maximum value achievable. So it's the optimal solution if the knapsack capacity was this small w. Of course, our goal eventually is to find out what K of big W is, because that is the original problem's capacity, right? So now, what we'll do next is we will try to express this KW in terms of smaller subproblems. So remember, we have to recursively define the subproblems in terms of even smaller subproblems, so that we could do the recurrence relation, right? So to do that, imagine that we have the optimal solution for this capacity W. So whatever this capacity is, there's an optimal solution for that. And there is some item X in that solution, right? Let's say there is some item X. We don't know what that item is, but there is that item X. Now, if we remove that item X, okay, if we remove X from that set of items, we will get the optimal solution to K of W minus the weight of item X. So let me show you an illustration. Let's say that currently the capacity is, we are looking at weight of let's say 5. Okay, and currently the best that we could do is we have A, B, or let's just make it capacity of 6 or even 7 so that we have more items to add. Okay, if it's 7, let's say that so far the optimal solution is taking item A, item B, and item C. So maybe this one has weight 2, weight 4, and weight 1. Okay, so maybe this is the current optimal solution for capacity 7. Now, let's say that our item X was item C. If we remove item C, the remaining items here should still be an optimal solution to a smaller subproblem, right? So if we remove item C, then the total weight would just be 6, right? And AB lang, so 2 kilos and 4 kilos, this should also be the optimal solution for W is equal to 6. Because if it's not, then we would have had a different optimal solution for W is equal to 7, right? If there was a better combination than this, that better combination plus this 1 kilo would have been the optimal solution, right? But since this was the optimal solution for 7, removing this would give us the optimal solution to 6, right? Does that make sense? So if you remove X, you get the optimal solution of weight minus the weight of X. So if you have 7 minus the weight of C, which is 1, we get optimal solution for 6, right? Now, if we have removed B this time, it would give us the optimal solution for weight is equal to 3. That would be A and C. So this one is 2 kilos plus 1 kilo if we remove B. Okay, so that is the property of dynamic programming subproblems, right? It has optimal substructure, wherein the smaller subproblems contribute to the solution of the bigger subproblems. Okay, now once we have removed it, adding the item X back should give us this total value, right? So let's say, for example, from 2 kilos, 4 kilos of A and B. So this is for weight 6. Now, if we added the new item X that we removed just now, if we add it back, so this will make it the optimal solution for W is equal to 7, right? And that would add the total value of plus X to the total value of this one already. Okay? So, why Vx? Because that is the value of item X, which we just added. Okay? So, if it was not in the solution, this would be the value, right? The optimal value. Then, if we add the item X, we would add plus Vx here. Okay? So, that is the solution, sub-problem that we will have for the unbounded knapsack version. So again, we can express Kw is equal to
W minus Wx, so weight of x, plus the value of x. So again, W minus Wx is, this is without the item x. So if it's not, if item x is not yet there, then we would look at the optimal solution for the weight without item x. But if we add item x, then we would add its value. Okay? But this is for some item x. We don't know what this item x is. And since we don't know which one it is, we will just try all items that fit the current W, current capacity, and select whichever is the maximum. Okay? So we'll select all items that fit. Okay? So, all in all, this would be the recurrence relation for the sub-problem. So, KW is equal to the maximum of KW minus WX. So this is what we showed earlier. The weight, the optimal value without the item, and then if the item is there, then you add the value of x. So, what is the maximum value for this equation for all items x that fits the current capacity W? Okay, so the weight should be less than or equal to W. If it's greater than the capacity, then of course it won't fit. So we will just ignore that one. Okay, so we'll try everything and we'll get whichever has the maximum possible value, because we're looking at maximizing the total value, right? So, okay. Before we could do that, we need to have a base case. So remember, the gutter values that we have, or the starting values that we need, so that we could actually start to propagate to fill in the other values, right? So the base case for this one would be if the capacity is 0. So if the capacity is 0, then there will be no item that would be less than or equal to the weight of the item is less than or equal to 0, right? So nothing would fit in the knapsack if it has no capacity. So, of course, the optimal value would be 0 as well, because there's nothing to put inside. Okay? So that would be the base case. Now, for the tabulation, we will keep track of 3 arrays, actually, okay, of size W plus 1. So, the first one is, we'll call that K. This will hold the optimal value of KW. Okay, why is it W plus 1? Because we will have from 1 up to W, and then we'll add the 0 for the base case. So that's why it's W plus 1. Okay, so the K array will hold the optimal value for KW. So this is the value itself. Okay, item array will tell us which item won the max operation earlier when we did the sub-problems. Okay, and then the previous array will tell us which previous sub-problem, the W minus WX, won the max as well. So this two, we will use this for the backtrace later on. And then this one, of course, will have the optimal value for the unbounded knapsack. Okay, and we will fill this from left to right, so from 0 to W. And of course, we'll fill up the base case first. So after that, we can already fill up the other sub-problems. Okay, so if there are no items that fit the current capacity, then of course that would be, we would add the value of 0 because we can't put anything, and then we'll just put null in both the item and previous arrays. Okay, if there are no items that fit the current capacity. So putting all of that together, this would be the pseudocode for unbounded knapsack. So you initialize the 3 arrays of size W plus 1, and then you initialize the base case, so K of 0, item 0, and previous of 0. So that would be 0, null, null respectively. And then we'll go from capacity from 1 to W, and we'll just filter out the valid items. So the items with weight less than or equal to capacity. So for each valid item, we will look at the previous capacity, which is capacity minus the item weight. So this is where your remember the K of W minus WI, or WI, whatever item.
So this is the previous capacity. Okay, and then that value would be the previous capacity plus the item's value. So you add the value of I. Okay, and then we'll add this to the choices, and we will get whatever choice is the maximum. Okay, and then the maximum value would be placed in K, the previous capacity would be placed in item, and then the previous capacity would be placed in prev, and then the best item would be placed in item. Okay, and then you do that repeatedly for from 1 to W, and once you've done that, we can get the final answer for K big W, which is what we're looking for. So if we try to analyze this running time, so this will run in capacity W, right? So this should run at most W times. Now this one, how many possible valid items are there? So since there are n possible items, the worst case that we could do is if all items are valid, right? So this should be n. So if it's W times n, and then here we're just doing O of 1 work anyway, inside times O of 1, so this would be O of n W, right? Ang running time niya. Okay, so back to yellow. So we're filling up 3 arrays of size W plus 1 from left to right, and each entry can take up to O of n time, because as I mentioned, all items could be valid. So there are W plus 1 iterations, and then O of n work per entry, so the running time, as I mentioned, is O of n W. And then the memory is O of W, because we are using arrays of size W plus 1. So it's only one dimensional, so O of W lang siya. Okay, so that's the analysis. Now, before we start with the backtrace, let me show you an example first of how this works. Okay, so for unbounded knapsack, we have the capacity of 10, and then we have 4 types of items with their respective weights and their values here. Okay, so this is how we'll set up the tables or the arrays. So we have 3 arrays: K, item, and previous. Okay, so at the start, of course, it would be capacity 0. So since there are no items that fit capacity 0, we'll just put 0 as the optimal value. Next, we'll have capacity of 1. Is there any item that fits capacity 1? There is none, because the minimum is 2, right? So we also cannot fit any item if the capacity is 1. So this would also be 0. Okay, because there are no items that fit. Now, how about if it's capacity 2? Now, if it's capacity 2, there is actually an item that fits already, which is item D, right? So even if we take the max, this is only the item that fits, so we will automatically get its value. So to get the value for capacity 2, if it's item D, so it's capacity 2 minus the weight of D, which is 2 kilos. So the previous capacity, if we remove D, would have been K of 0, right? Nothing would be left. And then you add the value of D, which is 9 pesos. So you have the plus 9. So what is K0? That is 0. And then plus 9, so you have 9. So this time, that would be the max, right? So the previous, so you put 9 as the value in K. The item that you took is the winning item, which is D. And the previous sub-problem is 0, which is found here. So you can think of the previous sub-problem as something like this. So what would be left in the capacity if I already took D? Okay, so like for example, let's change this to red first. Okay, so let's say, diba, our current capacity is 2, right? So we only have 2 kilos inside. And if we put D already with 2 kilos, okay, if we already have 2 kilos inside, how much would be left? So that would be 2 kilos minus 2 kilos, we have 0 kilos left. Okay, So that's why we have the previous as 0. Okay, so let's move on and go to the next sub-problem, which is now capacity equal to 3. And if it's capacity 3, now we have actually two items that could fit, right? If it could be D or it could be B, because B can now fit with 3 kilos. So if it's B, that would be 3 minus 3 plus the value 14. So we look at K0 plus 14. So we'll get 0 plus 14, so which is 14. And then for D, it's the same. Same thing. So 3 minus 2, we still could have 1 kilo left. But if we have 1 kilo left, there is nothing to put inside, right? So it still has an optimal value of 0, and then plus 9, we have 9. So we'll choose the max between the two, and that would be B, which is the max, right? So we'll put the value here, 14. B is the item that we took, and 0 is the previous sub-problem that we have. Okay? Now let's go to the next sub-problem, which is 4. What if the capacity is 4? Now we could put B, C, and D inside because they are all less than or equal to 4 ang ila weight, right? So if it was B, that would be 4 minus 3. So K of 1, this is still 0, so that would be 0 plus 14, still 14. D would have, D would have K of 4 minus 2. Okay, if it was 4 minus 2, so that would have K of 2, right? Which is 9. And then plus 9, we have 18. Okay, now if it was C, you would have had K 4 minus 4, that's K0, and then plus 16. So let me explain again what would have happened here. If we took B, the capacity was 4, right? W is equal to 4. If we took B, it has a size of 3 kilos, right? So 3 kilos ang take ta. So we have 1 kilo left. And in the 1 kilo, if you have 1 kilo free space, the optimal solution is, we know that to be 0. So 0, and then the value for B is 14. So we have the 14 here. And then for C, that would have been, C has 4 kilos, right? So you actually have nothing left in as a free space, right? Because you would take up the whole 4 kilo capacity. So for C, the value is 16, right? And if it's 0 kilos left, you have an additional optimal value of 0. So you have the 16 total. And if it was D, what would have happened is, if you have item D, you take 2 kilos, and you still have a free 2 kilos left, right? There's still a free space of 2 kilos. So the 2 kilos from D would be 9 pesos. And then we already know that the optimal value, if you have 2 kilos left, we have already solved that earlier, that is also 9 pesos. So if we add the 2, that would be 18. So this is how we computed these values. Okay? So we get the max, and of course that would be D here, which will give us 18 here. The item is D, and then the previous is 2. And then we'll repeat that process. So for 5, A still cannot fit, so it's still the same items, B, C, D. So we'll still compute the weight, capacity minus the weight of the item. So for this one, the maximum would be either B or D, right? But let's say we chose B for the tiebreaker. So and then after that, if it's 6, then item A can already fit, right? Because item A has a capacity of 6, and our current capacity is 6. Or sorry, the item A's weight is 6, and the capacity is 6. So it can still it can fit now, right? So if we compute it the same way, the maximum this time would be 30, and we have A as the item, and the previous sub-problem would be 0. So the explanation this time would be, if you had A, if it was 6, so you could take the whole 6 kilos of A, and there would be nothing left, right? 0 kilos of free space. But this would already give you 30 peso value, and then plus the 0, so this would actually be the maximum if the capacity was 6. Now if it was 7, Okay, if it was 7, what would be the maximum? It won't be A anymore because this time you could have um, either B or D as the maximum, right? Don't take A, but instead take B and a D. So B and a D would give you, or sorry, B and two Ds, right? Is that right? B and two Ds. Yeah, B and two Ds would give you 14 plus 18. Yes, that's 32. Okay, so item B would be the best to take here. And then if it's 8, the maximum would be A this time. Okay, so you would fill up these values. And then for 9, you would get either A or B. So let's just choose A for the tiebreaker. And finally for 10, we would have either A or D. Then just choose A for the tiebreaker. So we know now that the best possible value, if we have this set of items and the capacity is 10, is 48. So this is actually the previous example that I showed earlier, right? Now, what will we do for the backtrace? For the backtrace, to actually get the combination of items that gives you the unbounded knapsack solution, we'll start at the capacity big W, which is the original capacity, and then we'll get the item there, and then we'll follow the previous of that capacity. Okay, so we'll repeatedly follow the previous while getting each item at that index. Okay, so we'll repeatedly do that and until we get a null as the previous. Okay, so this will take at most O of W time, because the worst that it could do is traverse each item in the array, and our array is of size W plus 1, right? So it's O of W, worst case running time. So going back here, if we do the backtrace, then we could have starting from here, so we get 48. So we start at capacity 10, so we get the item A, and then the previous is 4, so we'll go to index 4, so we'll get item D, and then the previous is 2, so we'll go to index 2, item D again, then the previous is 0, so in 0 there is already null, so we'll stop. And so we now have the optimal items A, D, D with value 48. So this was the example that we had earlier. Okay, so let me show you one more example, this time with a smaller knapsack capacity. Okay. Okay, so what if it's like this? So I'll just go through this quickly. Just pause it if you have if it's going too fast. So at capacity 0, of course, you can't put anything, so the optimal value is 0. For 1, there is only one item that can fit, so automatically that will win. So this will give us 12. The item is B, and the previous subproblem is 0. For capacity 2, we have two items that can fit now. It would be B or C, and then if we do the computations, the maximum is actually item B. So this will have 24, item B, and the previous subproblem is 1. Okay, so we'll have previous as 1. And then for capacity 3, all 3 items can now fit, so we'll get the maximum. B will still win, and then the previous is 2. And then for 4, B will still win. Okay, and then for 5, B will still win the maximum. So you'll notice that B won all max problems, and that is possible, right? But that's not the case for all problems. So it's just for this type of problem, it so happened that B won all the max. So let's try to figure out the actual items. So we know that it has a total value of 60, but the first item would be B, and then the previous is 4, so that would also be B again. item of 3, B, item of 2, B, item of 1, B, 0, none. So we'll actually take 5 B's, right? So if you have 5 B's, that would have a total of 5 kilos, then 12 times 5 would be 60. That is the optimal value. And this is possible because, again, this is unbounded knapsack. There's an unlimited number of copies per item. Okay? So that's it for unbounded knapsack. Yeah. So this time, let's go to the other version, which is 01 knapsack. Okay. For 01 knapsack, for the brute force approach, we'll do the same thing. We'll find all possible combinations, and we'll reject the combinations that don't fit the knapsack, and we'll just return the combination with maximum value, right? But this time, how many possible combinations are there if we only have the 01 version? We either we only have one copy of each item. So if there are n items, remember that there are 2 raised to n possible combinations, right, from your ComSci 57. So like for example, if you have 3 items, if you only have 3 items, then we could enumerate everything. Okay, let me change the color. Okay, if we have 3 items, we could enumerate all possible combinations. So you could pick nothing, right? That's one combination. You could just pick the individual one, so it could be just A, B, or C. That's also a combination, right? You could pick AB, AC, BC, and then you could pick all 3, ABC. So this is another combination. So you have 1, 2, 3, 4, 5, 6, 7, 8. And that is exactly 2 cubed, which is 8. So that's 2 raised to n possible combinations. Okay? So it's exponential number of combinations. It will take constant time to check if it's a valid combination, because you just get the total weight and then see if it exceeds the capacity or not, right? So you have O of 2 raised to n as the running time for the brute force. But of course this is exponential, so can we do better than this? And I have run out of ways to say yes. So yes, we can do better than the brute force. So okay, so this time we are looking at the 01 version. So there are no more repetitions of the same item. So you either take the item or not. You can't take multiple copies of the item because there's only one version of the item this time. So the sub-problem for the unbounded knapsack cannot be reused or cannot be recycled for 01 knapsack because there are already different, 2 different problems, right? In unbounded knapsack, you were allowed to pick, let's say, item D multiple times. But in 01, you're not allowed to do that. You're only allowed to pick item D 1 time. So we have to tweak or change the sub-problem a little bit so that it reflects this difference. Okay? So we need to consider whether item X has already been used or not in the solution. So we have to be aware whether have I used item X already or not, because if I've already used it, then I cannot use it again. If I haven't used it yet, then I could possibly add it to the solution, right? So we will adjust the sub-problem to add information about the items that we've already used, okay? So what we will do is we'll add another parameter, we'll call it U, where U ranges from 0 to n, and what this will tell us is that if it's up to item U, then items 1 up to U are used in the solution. So if, for example, if if the U's value is now 3, then we know that items 1 up to 3 have been used in the solution. It's possible that okay, just to make it clear, okay, if U is 3, so that means that item 1, 2, 3, these are your choices in the solution. It's possible that 1 was not used because it's not optimal to use. It's possible that 2 was not used, maybe it was just 3. But the thing is, these are your only choices. So maybe you have other items here. These were not considered in the optimal optimal solution. Okay, only these items were considered, but again, that doesn't mean that all three items here were part of the solution. Okay, sila lang ang candidate choices. Okay, now if you have u is equal to 4, then that means that you considered up to item 4 for the optimal solution, but you did not consider this 2. Okay, so that's what we'll be using parameter u for. So we will adjust the sub-problem notation. Earlier it was just k of w, right? So remember, k of w was the maximum value if it has capacity small w. But this time we will adjust it and make it k of w u. Now what this means is it's still the maximum value achieved with knapsack capacity small w, but if we only use items from 1 up to this u. Okay, so we are now trying to limit the number of items that we'll use for that specific capacity. Okay, so this is the maximum value if we used only items 1 up to 2 or 1 up to 3. So that could change because the more items that you consider, the more options you have to add to the knapsack, right? So w will still range from 0 to big W, and then u will range from 0 to n. Okay. So obviously the goal eventually is to get k of w with n, meaning you're using all possible items. Okay, so or you're considering all possible items. Yeah. So our next step is to express kwu in terms of smaller subproblems. So for this subproblem, let's consider item u, or the last item that we considered in that series. Item u is either needed or not, right? So for example, if I'm considering, again, if u is, let's say, 4, then that means that I'm considering item 1, 2, 3, and 4. So let's say 5, 6, 7, and so on. But I'm considering up to here. So these are the items that I'm looking at for the current optimal solution. So it's either needed or not. Okay? If item 4 is needed in the optimal solution, that means that the optimal solution for this would be kw minus wu. So this part here seems familiar because this is what we used earlier sa 01 knapsack, right? Or sa unbounded version. So plus value. So this is again the solution or the optimal value without item u, and then we add the value of item u if we add it to the value. But if it's not there yet, then we only considered up to u minus 1, right? So without item u and then with item u. So without item u, this would have been the optimal solution, right? We'll reduce the weight, so without the weight of item u, and then we'll reduce the number of items we considered as well. So u is not considered, but only up to u minus 1. Okay, and then once we add item u, we will add its value. So more or less similar to the previous subproblem, and that is if item u is needed. But if it's not needed, then the k of wu would be, so if this is not needed anymore, then we could just consider up to here, right? So that would be k of w still, because if it's not, if the item is not part of the solution, then we will still have the original capacity, right? We're not reducing the capacity because anyway, item u is not a part of the solution anyway, right? So it's still the same capacity, but we're just reducing the number of items that we considered. So since we know that item u is not part of the solution, then we'll just look at from u from 1 to u minus 1. Okay, so we're reducing the items we consider. That is if u is not needed. So those are the two possibilities. You either need item u or not. And since we don't know whether we need it or not, then we will try both cases and we'll get whichever gives us the maximum value. Okay? So, for item U at capacity W, we'll get the maximum of these two values. So, either K, W minus weight of U, then considering up to U minus 1 lang, plus the item value, or we could just get the same capacity with without item U, so up to U minus 1 lang, and then we'll get whichever is maximum. So once we do that, we will be able to tabulate and create 3 tables this time. So earlier we only used a one-dimensional array, right? But this time we'll have a table because we have 2 variables to consider, right? The capacity and the number of items, so W and U. So we will have 3 tables with size with the following size: W plus 1 rows and N plus 1 columns. So we have the capacities at the rows and then the items at the columns. So we'll name these tables K, that would hold the optimal value for KWU. Item would tell us whether to include the item or not, and then the previous would be used for the backtrace, so it's the previous WU coordinate. Okay, so now for the base case, it would still be 0 if either the capacity is 0. So if the capacity is 0, that means that you can't put anything, right? Because the capacity is 0. And if item is if U is 0, that means that you cannot use any items because you are not allowing any item to be considered. So if there are no items to be put in place, then you also have 0 as the optimal value. Okay, so you'll put that at the gutter values as well. Okay, so putting all of that together, okay, so let me show you the base case first. So for this one, you'll notice that this is the gutter value, so 0, 0, and then null for the rest for I and P. Okay, okay, so putting all of that together in a pseudocode. Okay, so it would look something like this, right? So we'll initialize the 3 tables of size W plus 1 by N plus 1, and then for each row we'll initialize the base case, so this will take W times because it's from 0 to W. And then for each column we'll also initialize the base case, so this will take N time. And then this is the main loop for the tabulation, so we'll go per row and then from left to right. So this is going per row, so this is from 1 to W, so this will take W time. And then per column from left to right, so from 1 to N, so this will take N time. And then for inside, this is just comparison, right? So this will take constant time, O of 1. So if the item cannot fit, then obviously just get capacity U minus 1 because it cannot fit anyway. So just look at the previous sub-problem, and then if it can fit, then you choose whether to include it or not. Okay, if it's better not to include it, then you choose the values for not including it, and if it's better to include, then you choose these values. So not including it means that you're looking at current capacity U minus 1. If you include it, you check the previous capacity wherein you subtracted the item's weight, then U minus 1, and then you add the value. Okay, so you compare which one is bigger, to include it or not include, and then decide based on that. And then after you've done the tabulation, it will run in you return K of WN, which is what we want. So in total, the running time for this would be, the first loop is W, and then you add the second loop, which is N, and then you add the third loop, which is W at the outer loop, and then times N at the inner loop, times O of 1 for each iteration. So that would be O of NW still, running time niya. Okay, so okay, so For the analysis, again, we're filling up 3 tables with size w plus 1 and n plus 1, and each entry takes O of 1 computation, so it takes O of nw time in total. And then of course the memory is also O of nw because we're using 3 tables of that size. Okay, now before we discuss the backtrace, let's look at the solution. Let's look at the example first of how to compute the value itself. Okay. Okay, so after we've finished filling up the base case, we can now start at 1, 1. Okay, so that means that the capacity is 1, and you're considering only from items up to item 1, which is A. Now, if it's capacity 1 and you're only considering up to item A, which is 3 kilograms, it cannot fit, right? So we'll just look at the previous sub-problem, which is U minus 1. Okay, so that would be 1, 0. So that would be 1, 0. It's this one. So that item is 0. So you'll put that there. So that's the previous 1, 0. Okay, and then you don't take the item because, well, it did not fit. For the next one, capacity is 1, and then you're considering up to item number 2, which is B, and this time B can fit, right? So you can choose whether to include it or not in the solution. If you don't include it, you'll just go to the WU minus 1, so that's 1, 1, so the previous cell, so that's 0. But if you include it, then the W minus WU, that would be 0, because 1 minus 1 is 0. And then U minus 1 would be up to item 1 only, and then plus the value of 12. So K of 0, 1 is 0, and then plus 12 is 12. So of course the maximum value would be this one, so you can choose to include it. So the previous coordinate is 0, 1, and you include the item B. Okay, and then for item C, it cannot fit, so obviously you just look at the previous, because anyway hindi man siya ka-fit, right? There's no point in considering C, so you'll just take or copy the value for the left value, so 12. Okay, and then 1, 2, and then it's not added. Now for the next row, A 3 cannot fit 2 kilos, so just copy the previous, so it's 0. Here 1 can fit 2 kilograms, so you again decide whether to include it or not. So just follow the computations here. So 2, 1, so that's the left, it's 0. And then K of 1, 1 plus 12, so that's 0 plus 12 is also 12. So we'll choose that one, because that is the maximum, right? And then the previous cell is 1, 1 here. And then you have the item B. And then if we have capacity 2 and then up to item 3, then item C could be put inside, right? So if we don't include it, that would still be just the left cell, so 12. But if we do include it, so 2 minus 2 is at weight 0, so that's here, and then to the left, so without considering C, so that would be 0, and then plus the value of C, which is 20, so 0 plus 20 is 20. So that would win the max. So that means that 0, 2 is your coordinate, and then you add the item C here. Okay, so we'll go to the next row. This time A can fit, right? Because it's already 3 kilos. So you can choose whether to include it or not. And if you don't include it, it's still 0. But if you include it, that would be 0 plus the value of A, which is 35. So that would win, obviously, 35. So the previous would be 0, 0, and you have the item A. For this one, if you don't include it, it's 35 ang B. If you do include it, the previous sub-problem would be 2, 1, right? This one. And then plus 12. So this time, the optimal solution would be not to include item B. Okay, so what happened here? For this one, okay, let's try to illustrate the details of this. So currently we have W is equal to 3, and if we include item B, if we include B, if B is in here, in the knapsack, B would take up how much weight? 1 kilo, right? So the free space left would be just 2 kilos. Okay? And 2 kilos while only considering item from A. These are your only choices because you've already added B inside, right? So if you have 2 kilos with only A as the possible solution, so 2 kilos with only up to A, but since A cannot fit because it's 3 kilos, so you would have an additional value of 0. So you cannot put anything. So you'll only have the value of B, which is 12, and then additional of 0. So that would be 12. But if you did not include B, so if B is not there, then the free space would still be the full 3 kilos. Okay? And 3 kilos while you consider only A, because if we don't include B, then we can only consider A from the items because we are only considering this 2, right? And if it's this is not part of the solution, then we'll only consider this one. If you have 3 kilos and you can put A, you can actually put that inside, right? 3 kilos and you can only put up to A, the optimal value is 35 by putting in A. So 35. So you have a total value of 35 here by not including B, and if you include B, it will only have a value of 12 because you cannot put anything anymore once you add B, because the 2 kilos that would be left cannot fit the item A anymore. Okay, so that is why the winner for this one is not including item B. So 35, 3, 1, and then you don't put the item. Okay, so that's the explanation. And then for 3 kilos with considering item C, so if we don't include it, it's 35. If we do include it, that would be 12 plus the value 20, it's 32, but 35 is still better. So we'll choose 35 and then don't put the item. Okay, so we'll go through the next row. So for 4 kilos with only up to item A, so this time it would be if we don't include it, that would be 0, right? If we do include it, that would be 0 plus the value 35, so that would be 35. If we add up to B this time, if we don't include it, that would be 35. Now this time, if we do include it, right, if we include B, where our capacity is already 4, if we include B, if B is here, it would take up 1 kilo, right, with a value of 12. So the free space left would be 3 kilos, and you'll consider items from A lang because you're only considering A to B, and then since you've already added B, then you can only add A. If you have A with 3 kilograms, then you can add A with a value of 35. So this will actually give you total value of 47, which is better. So we'll choose 47, and then the previous subproblem is 3, 1 here, and then you put the item B. Now, what if you include up to item C? If you include up to item C, this time, what would have happened? So if it was including item C, because if you don't include it, it will just look at the previous subproblem, right, 47. But if you don't if you do include it, put C there. If you put C, this would give us 2 kilos and 20 peso value. So if you this is W is equal to 4, not C. So if you're already taking 2 kilos, we'll be left with 2 kilos free, and you consider items A and B, right? Because you cannot consider C anymore since it's already been added. And if you have 2 kilos with up to B, that would be here, right? So 2 kilos and then up to item B. So the optimal solution would just be 12, because that would be adding B lang. Because you can't add A because it won't fit the 3 kilos won't fit inside 2, right? So you can only add B here. This will give us 12, right? So 12 plus 20, this will only give us the value of 32. So this is actually not optimal. So just choose not to include C in that case, because if you don't include C, you have more room to put B inside, right? So the previous one. So therefore, the optimal value for this one will be 47 and not included. And then for the last row, we're now at the last row. So if we don't include it, it's 0. If we do include it, it's 35. So we'll pick 35. And then up to B, if we don't include it, it's still 35 from the previous problem. But if we do include it, that's 35 plus the value of B, which is 12, is 47. So of course we'll pick 47. And finally, if we don't include C, so this time, this is the last sub-problem, so I'll illustrate it again. So W is equal to 5, and we're considering up to C, so A, B, and C. If we don't include C, so if C is not there, then we're only considering A and B. Okay? So we already know this sub-problem. Weight is equal to 5, or capacity equal to 5, considering only A, B. So that would be 5 tapos up to B, which is this column. So that is 47. So we know that the optimal value for this would be 47, and that is if you add A and B itself, right? Because A would have 3 kilos, B would have 1 kilo, right? And that is because you chose not to include C in this case, right? So, but what if we did include C? Include C. So if we add C here, C will take up how many kilos? 2 kilos with a value of 20. So we're actually left with how much free space? 3 kilos free space, while only considering this time A and B, because we've already used up C, right? So 3 kilos with only up to B, that would have a value of 35, because that would be only adding A, because A would give you 3 kilos as well. So this is 35 pesos. And if you add the 2, that would be 5 kilos, which fits our capacity. And the total value is now 55. And this one is bigger than 47, so we'll of course pick this one, 55. So 55 is our final optimal value. The previous is 3, 2. So that's why we have that here, the 3, 2 here. And then we have item C. Okay, so we now know that given this scenario, if we have 0, 1 knapsack, the optimal value that we could get is 55. But how will we get the actual items that will give us 55? So this is where our back trace will come in. So we'll start at the bottom right at WN, and then we'll get the item there if it's not null, and then we'll follow previous of that coordinate until the previous is null as well. So similar to what we've been doing so far. Okay, just follow the what we saved in the previous. Okay, so this will also run in at most W plus N, because the explanation here is that you could move one column and one row per iteration at most. Okay, so that would be W plus N. So if you move one column per iteration, at least one column per iteration, and then one row per iteration, that would give you W plus N. Okay, so still more or less linear time, so it should take it should not take as long. So given that we had this problem, so going back here, so if we follow the back trace, so we'll start at 3 2, so the item there is C, and then we'll go to the previous, which is 3 2, sorry, the first coordinate was 5 3, the bottom right, okay, and we have item C here, and then we'll follow the previous, which is 3 2 here, but there is no item there, right? And then the previous niya is 3 1, so to the left that would be 3 1, so the item there is A, and then the previous of that is 0 0, and then there is null, so we'll stop here. So we have found out that the optimal value is 55, and the items would be A and C. So if you add A and C, that would be 5 kilos, and then the value would be 35 plus 20, which is actually 55. Okay, so that is 01 knapsack, and yeah, that's it. So to review, we have discussed dynamic programming, and the elements of dynamic programming so far is that we divide it into sub-problems, but the sub-problems are overlapping, okay? And then once we have formulated the sub-problem, we'll express it in terms of smaller sub-problems. So you find the recurrence relation, and the sub-problems have an optimal substructure property, wherein the optimal solution for the smaller sub-problem contributes to the optimal solution of the bigger problem, okay? And then after you've set up the recurrence relation, then it's easy to actually create the to compute the optimal value using tabulation. So you usually go per row from left to right, so that you can compute the values quite easily, because you're just basing it on previous sub-problems, okay? And then to get the actual optimal solution itself, you have to keep track of the backtrace, because you'll only be computing the optimal value, right? Just numbers. But if you want the actual combination or the actual sequence, then you have to keep track of the backtrace and do a separate procedure to recreate the optimal solution itself. So to recap, we discussed minimum edit distance, wherein we used prefixes of x and y as the sub-problems, and then we used this sub-problem, minimum edit distance of A and B, so we looked at their prefixes, and then we just choose the minimum of A minus 1B plus 1, A B minus 1 plus 1, then A minus 1, B minus 1, and then the difference, okay? So whether we align it as an insert, a deletion, or as a substitution. So since we don't know which one is the best alignment, we'll try all three and then just get whichever has the minimum value, okay? And then we also discussed longest common subsequence, wherein we also used prefixes of x and y, so pair of prefixes, to get the LCS of x and y. And then if the last two letters are equal, then we'll look at LCS of A minus 1, B minus 1, and then the plus 1, since there's something in common. But if they're not equal, then we'll just look at either A B minus 1 or A minus 1B, and then we'll get whichever is the max, okay? And then for longest increasing subsequence, we'll just look at the prefix of A, and then we'll look at the previous items that are supposedly increasing with the current item, so from 1 up to x minus 1, so all the previous items that are strictly increasing, okay? And then we'll get whichever has the max LIS of previous plus 1, okay? And then for unbounded knapsack, we look at smaller knapsack capacities as the sub-problems. We'll use KW to denote max value of item combination that can fit capacity W, and then we'll just get the max of K W minus W X, so this is without item X, and then if we add item X, then we add its value, and then since we don't know which item X that is, we'll try all item X's, and we'll get whichever gives us the max, okay? But of course, we'll only consider items that fit the current capacity, okay? And then for 01 knapsack, we'll just tweak the unbounded version. We have to consider which items we've already used so far, so you have an additional parameter u, which denotes the items that you've used possibly in the solution. So kwu tells us the maximum value of item combinations that can fit w capacity using items from 1 up to u. And then similar to the previous one, we'll use either kw minus wu, u minus 1. So if this is not with item u, and then if we add item u, then you add the value. But if we don't need item u in the solution, then we'll just look at the previous sub-problem where it is still the same capacity, but we don't consider item u in the solution. Okay, since we don't know whether we should include u or not, then we'll try both cases and we'll take whichever gives us the max value. Okay, so that is dynamic programming. And if you have any questions, don't hesitate to ask me. There are some demos that I've also provided as a separate video, and you can watch that, and you can watch it slowly or you can pause it, just so you can see the step-by-step process more in a more detailed manner. Okay, so that's it for this video, and I'll see you next time.